Good morning, everybody. Welcome at the University of Florence. Today we are here for a workshop on Google Earth Engine and application of remote sensing in different areas. I go immediately to present an introduction. Here we are. We organized this presentation and workshop within the framework of the Copernicus Research Unit at the University of Florence. So just a few words to introduce our activity. Okay, we know that nowadays remote sensing are one of the main areas of big data. Sometimes we say that remote sensing is big data ante litteram, in the sense that they started to be big data even many years before then we started to use this term of big data, because we acquire information from multiple sources of information, multiple satellites, with frequent acquisition of daily new fresh data. So a large amount of information available. To fully understand these, the information that are within these data, we need new technologies to analyze large amount of data. So without this kind of hardware and software resources, we are not able to fully understand the information that are inside the data. So a big step, a big advancement in this area is the introduction of cloud computing opportunities. To do so, we have to integrate different backgrounds. So scientists in different areas have to cooperate together, both coming from information and communication technologies, with remote sensing specialists and scientists working in the different application areas. In this framework, Google Earth Engine is a game changer in the sense that for the first time we have a platform that is able to offer the opportunity to use large cloud computing opportunities for everybody. The Copernicus Research Unit in Florence, born in 2020, it's made up of 8 departments of the University of Florence. You can see the list of the departments that are cooperating in this multidisciplinary infrastructure of the University of Florence. So you can see the Department of Agriculture, Geology, Architecture, Mathematics, Informatics, Engineering, Statistics, and Geography, cooperating together in the area of application of remote sensing. Our aim is to offer new opportunities for researchers, so to use advanced methods for remote sensing application in research, and for transferring these research activities to teaching, so to our students. The Copernicus Research Unit at University of Florence is connected with several nodes that are outside of the University of Florence. Two of the most important are the Copernicus user uptake infrastructure, and we will see a presentation after all, and the Italian Society of Remote Sensing. So, today we are going to have two moments. In the morning, we will have the presentation after this very short introduction. We have the introduction from Andrea Taramelli, who is responsible for the Copernicus User National Forum. Then we will have the keynote speak from Noel Gorelik from Google Earth Engine. At 11 o'clock, we will start to present some application of Google Earth Engine technologies in different areas, developed both within the framework of the activities of the University of Florence or from other research institutions working with Google Earth Engine. Then we will have a very short break at 11:30, and then we will have a little bit longer break for lunchtime, so that we will start again after the lunch break at 2:30. And we will have in the afternoon two sessions that are basically a workshop, so an introduction to the how to use Google Earth Engine. And these will be presented by two young researchers here at University of Florence, Saverio Francini and Giulio Castelli. You can interact with us. Posting your questions with short messages and WhatsApp with this telephone number that you can see there. Sometimes during the YouTube, we will have some moment where we will show again this telephone number. I will group all the questions in order to give to pass the questions to the people, to the speakers at the end of the session. So at the end of before the coffee break and before the lunch break. I have to acknowledge the work of a large number of people who cooperated in organizing this day. So you can see here the names, Costanza, Francesco, Saverio, Francesca and Giulio. But there are a lot of colleagues who helped us in organizing this networking and workshop day. You can see there some links, the links for our research group, the Copernicus here at the University of Florence, our laboratory, GeoLab, the Laboratory of Forest Geomatics, and the link of the YouTube, where you will find also after this day online the presentation that will be recorded during this day. Okay, I hope that you will enjoy staying with us. So write us through the SMS and WhatsApp. And so now it's time to give the floor to Andrea Taramelli. So I go back here. Andrea, do you hear me?
Thanks.
Okay.
Yes, I can hear, and thanks, Gerardo, for inviting me. I will make a very brief speech, and I would like to endorse all the activity that the Copernicus unit at the University of Florence for the Copernicus Academy is doing. As a national delegate, I will put some, major point, and a major question is mostly related to how this, testing and playing with Google Earth Engine and all the use cases that you are going to present can be part of national strategies that we are setting up at national level. So I will share if it's yeah. Can you hear? Can you see the presentation?
Yes, we can.
Okay, perfect. So, as most of you already know, that the Copernicus is a European regulation that is going to be renovated again for other 7 years at European level. So, as we all know,
Andrea,
it's made by...
Excuse me,
Yeah.
Can you put in presentation mode? Because we see very small slides.
I put in presentation mode, so let's try another way.
Maybe you have to share the full screen.
The full screen, yeah.
Yes.
Yeah. Let's see. Yeah. Now it's better. Whoops.
Perfect.
Yeah. So now you see the full screen, right?
Yes, we can.
Gerardo, can you confirm?
Yes.
Okay, so the Copernicus ecosystem, it's quite wide. So the point is not like only focusing on the data, but on the information that are really needed at the end for implementing operational services. So you have policymakers, spin-off, ICT players, but you have also energy utilities, companies, investors, aerospace, and also university and research. So I always like to show the value chain that is made as a very wealth trees, where you have the upstream that is not the top, but is the bottom of the trees, and then you have midstream, downstream, all the user uptake and the end user. So the point is that events like the one of today are completely in line of the user uptake strategies. So we have always to consider that the upstream part, that is, the bottom part, is also not made just by, Earth observation data, so satellite, but is also about in situ observation and all other type of information. Then we have all what we call the midstream, so all the Copernicus services and also all the DIAS infrastructure that are, some sort of like open and unique point for getting all the data information of all the Copernicus trees. Then, as I was underlying, all the strategies is really made up by the network and all the activities. And today you are working as a Copernicus Academy, so you are involving different players. But we have to really think that the value chain is really focusing on the real end users that are non-Earth observation experts. So what I'm asking and putting as a discussion at the end of the presentation that you will have today is that how you're going to play and how you are going to stimulate the Copernicus marketplace development. So you have like a different Lego that you have to play with. So all the use cases you are going to present today has to make unique strategies that are elaborating very disparate data. So, Earth observation, demographic, sensor technology, social, all this type of information, changing a paradigm that are not any longer just focusing on what we call the big data, so employ multiple data sets for all together. But what we are looking as a marketplace and an uptake to get all the non-Earth observation expert end user to use all the information that we have to produce more value but less information. So real-time, precise, global scale, and predictive. So based on this playing and playground, what we are envisaging is a different business model of existing services. So as is, you have like a phase where you have customized services. So you will present a lot of these customized services in the example. But the available services, and especially the available tool, has to be more elaborated in a way of producing thematic and transversal services. You have always to think that the market uptake, so the market strategies that all the Copernicus Academy and all the network we are interacting with has to develop a marketplace for horizontal approach, more the unique and vertical approach with a more flexible services and models that can be adapted by different users in multiple contexts. Based on that, we have produced a quite huge investment at national level when we have built national space economy strategies, a mirror Copernicus investment to build up what is the Copernicus marketplace. So one of my questions will be, how many of the use case that you are going to present today can be useful for the 8 national thematic services that will be developed with like a 450 million euro investment in Italy for the Copernicus marketplace, and which are the buyer group that can be interested in all the development that you are going to propose today. So the marketplace strategies is really want to produce a public-private partnership using all the development that the Copernicus Academy, but all the people presented today will contribute to produce a unique marketplace at national level, but also at European level. But take in consideration that what I would like to know, how many models and algorithms that you are producing and presenting today can be translated in these market uptake national strategies to put into the thematic services, and then in a task tiers for the use of multiple end users. So I leave the floor to the discussion and to all the presentation, because I think that the day of today can really produce really good ideas in that market uptake strategies. Of course, I don't have enough time, but I would like also to have a feedback from Noel in that sense. How much the Google engine can, let's say, support these strategies in this Copernicus environment. And then I leave the floor, and I really thanks Gerardo for inviting me, posing all these questions at the very beginning of the day.
Okay, thank you very much, Andrea, for your presentation. Thank you for staying in very short time. Yes, I think that there are a lot of questions regarding the future, in the sense that the world and the market of remote sensing is evolving very, very fast. I think that 10 years ago it was difficult to imagine the development of remote sensing that we are facing in these days, at least for my personal point of view of a researcher. So it is a really interesting question regarding how, let's say, how these investment that and the world of the space agencies, such as the European Space Agency or the Italian Space Agency and so on, can cooperate in the future also with private companies such as Google, for example. This is a very interesting question also for us, for researchers. I don't know, maybe Noel, at the end of your presentation or whenever you want, you will have the time to tell us, if you want, if you can, regarding the future, because of course we are very very happy to be able to talk with you regarding also future development of this word. Okay, I think that we are receiving some messages, but they are mainly for appreciating the day, so no question for the moment. So even if we have some minutes in advance, I think that we can give the floor to Noel, so you can have some minutes more for your presentation. Do you agree, Noel? Okay.
Sure. I hope I have enough content to fit in the time allocated. We'll see how that goes. And if not, then maybe a lot more time for Q&A.
Okay, the floor is yours, Noel.
All right. I will also attempt to share. We'll see how that goes.
Okay, it's arriving.
How's that?
Yeah. It's okay.
Alrighty, great. So thanks for having me. As you might have seen by now, my name is Noel Gorlick. I'm a software engineer here at Google, and coincidentally, a PhD candidate here at University of Zurich as well. Before I came to Google, I was the software guy in a remote sensing laboratory. I got to work on 6 NASA Mars missions. That was every American Mars mission after Pathfinder that didn't crash. So that was a fun introduction to my career. And then Google gave me the opportunity to come take everything I'd learned and apply it kind of however I saw fit. And Earth Engine is more or less the product of that meeting between me and Google. I've been here more than a decade now, and I've, in addition to working on Earth Engine, I also worked on Google Mars and Google Moon, which I'm sure everybody is very familiar with and gets to use in their daily lives. And I'm also a member of the Landsat science team and recently the JEDI science team. So Earth Engine is the product of coming to Google and trying to do big data analysis on Google's infrastructure. So Google has got millions of CPUs, but it's common that when you start at Google, when you get hired as a software engineer at Google, you are completely useless for 6 to 9 months because it takes specialized skills to be able to make 1 million CPUs do what you want effectively. And that, as a software engineer, that's fine for me to have to learn how to do that. But as a scientist or a person trying to build a commercial application, it's ridiculous for you to have to spend 9 months to learn how to make a bunch of CPUs do what you want. So Earth Engine is sort of the middleware that sits between Google's giant parallel processing system and scientists or application developers who just want a place to be able to process some data without having to have a PhD in computer science. When we were designing Earth Engine, our #1 goal was to make it as easy as possible to do the common operations that happen in remote sensing. Things like getting data and processing it, dealing with file formats and projections, managing lots and lots of CPUs and disk. I like to think of myself as a scientist and a very specialized engineer, but ultimately at the end of the day, I'm really just an IT guy. I happen to be an IT guy for several 100,000 users, but what I've learned how to do over 30 years is move data around, process it, work on it, and Earth Engine is the way that I can make it so you don't have to learn those things as well. So in addition to making it easy, I want to make it easy for you to be able to build apps, build tools, and then make them scale to ridiculously large proportions, but most importantly, to make them shareable. As a scientist, you might know how to make a drought detection tool or maybe you're specialized in pygmy elephants and you know how to build a tool to track and detect them. What I want to be able to do is make it easy for you to do your science and do your work and build tools to do these specific tasks. But then I want you to be able to share those as easily as possible and share them with people that wouldn't normally have the skills to do the drought detection. There's a lot of people that need to know when a drought is coming, but not that many people that are able to predict it very well. So I'm trying to enable scientists and application developers to then enable many, many more non-traditional users, people that would never have been able to use remote sensing data without some intermediary between them and the data. The Earth Engine team is about 20 people. It fluctuates a little bit, but a full quarter of that team is focused on trying to use Earth Engine specifically to address society's biggest challenges. And for us, that looks like deforestation, drought, disaster, disease, and climate change and sustainability. I won't even pretend that I know how to solve any of these problems, but I know people that are working on them. And my job is to go out in the world and find laboratories and universities that are trying to solve these problems and then supercharge their work, make it as easy as possible for them to get this kind of work done, and then make a scalable and shareable workflow that they can share with people that need it. So that's the basic philosophy behind Earth Engine. Make it easy to enable absolutely everybody to use Earth Engine or Earth observation data. One of the things that makes Earth Engine very attractive and makes this an easier task is that we have an enormous data catalog that we've been collecting over the past 10 years. It's currently about 750 data sets spanning more than 40 petabytes of data. And that's both raster data and vector data. Most of that is satellite imagery, just because that's the biggest data streams, but there's a bunch of other data sets in there to use as well. And all of that data is in a form that's ready to use. You don't have to download, you don't have to worry about file formats or projections. You can just point at a data set and start using it. And we curate these data sets. So there's a relatively high bar for getting a data set into Earth Engine because we go through a lot of steps to make sure that data is ready to use and has all the information you need to jump in and start using it. Many of those data sets are constantly updated, the ones that update frequently. Some data sets only put out one data product a year, and so we keep those updated when we can. But some data sets, like the Sentinel data and the Landsat data, are updated multiple times a day. We're currently adding about a petabyte per month to the data, and in the last year we added about 100 data sets, and that's a relatively constant upward increase in the number of data sets. All the data sets that are in Earth Engine are there because a user asked for them. So we very, very infrequently go out and just proactively load a data set. Essentially, the user community votes on what they want next, and then our data team goes and tries to bring that data in. It's certainly the case that there's a lot of data out there that we won't be able to get for you. Commercial data that needs to be bought and we can't transfer a license for, or just private data that you've collected on your own. So you can always upload your own data into the system, and that data is private to you until you want to share it with other people, but you can use it just exactly the same way that you use our data sets. All the data is kept in a nice, pretty data catalog. Here's the front entry page for that. And since there are 750 data sets, there are lots of different ways to search through that data, including tags for specific providers, satellites, themes, that sort of stuff. Here happens to be the page for data sets tagged with Copernicus. And every single data set has a data set description, which tells you about the data set, what's in it, how the bands are scaled, any properties, if there's a citation or a terms of use limitation, DOIs, things like that. All the stuff you'd hope to be able to see about a data set. A quick tour through 750 data sets is tough, but the bulk of our data is, as I mentioned, satellite imagery. primarily from the Landsat and the Sentinel satellites. But there's also quite a number of other satellite sensors that we have data for. But then we also have things like climate and weather data sets, but even forecasts, things that don't necessarily come directly from a sensor, but are modeled data. And here's an example of a few. And then a bunch of other things like geophysical data sets. There's 29 different kinds of terrain data sets and 21 different land cover data sets, plus many, many more. And like I said, if there's data that you would like to use in Earth Engine that we don't have, you can just ask for it, and our data team will consider whether it's something we can get or not. So how do people use Earth Engine? Ultimately, Earth Engine is just a web API, a REST API. You're passing text messages between your computer and our computers, telling them what to do. You can do that by hand, but it's pretty terrible. And so most people end up using the Earth Engine code editor. This is a web-based graphical user interface for developing code for Earth Engine to run. It's got a map for displaying results, a place where you would provide code, and then inspection tools and examples and all the stuff that makes a user interface nice. Here's an example of applying that user interface to computing seasonal phenology. So you can see we've got basic charting. The code is in a relatively nice editor, pretty maps. So about 90% of all of our users use this interface because it's designed for the novice. It works pretty well for experts, but with less than an hour's worth of training, many people can come up to speed and start working in this interface, even those with little to no programming experience. There's also the possibility of using Earth Engine from within Python. There's a Python client library, and people have migrated this into IPython notebooks. And so in the data science world, IPython notebooks are popular, and we try to enable Earth Engine in there as well as we can. But things get a little bit tricky because a lot of people see a slide like this and they go, Python, great, that's what I want. I'm going to go to town with Pandas and SciPy and NumPy. I know how to use those. I'm just going to jump in and use those. It doesn't quite work that way because everything that you do with Earth Engine involves building up a description of what you want to happen and then sending that off to our servers. And our servers then process it using parallel processing and things that don't know anything about Python. So while it's possible to use scikit in your analysis, the back end can't. And so there are limitations on what you can send us to do the processing. And if you want to use Python-based tools, typically you'll have to bring that data back to your computer to then work on it. But we enable that. A recent development that has made it easier to use Earth Engine is one of our users has developed a QGIS plugin that works very similar to the IPython notebooks, where you in this case, provide Python. The Python is executed within QGIS, builds up a description to send to Earth Engine. Earth Engine then runs the results, and then you bring back tiles to display along with other data sets that you might be using within QGIS. And it works pretty well. It has the same limitations as Python and even the JavaScript in that you're not able to, for instance, use a random QGIS plugin against massive petabytes of data, but data that you can process in Earth Engine, you can then bring back into QGIS and use tools like scale bars, things to make maps pretty and ready for publication. And then often people want to use Earth Engine, but they don't want their users to know that they're using Earth Engine or to have to deal with the fact that they're using Earth Engine. So what we've done is we've enabled Earth Engine apps. So once you get Earth Engine working and detecting what you want to detect, say maybe you build a drought detector, you can then click a button and we will turn your output into a web app, complete with user interface components, scale bars, legends, buttons, those sorts of things, all with a couple of clicks, so that you are able to deploy your results to a wide audience without them, one, needing to be Earth Engine users, or two, being able to muck with your code. It's not perfect that people can get to your code if they really want to. So it's not a secret or a secure way, but for the average user that you just want to be able to provide results to, it's a very easy way to build a web application without needing to be a web application developer. Here's an example of just a couple of the many tens of thousands of user applications that people have built with Earth Engine apps. This first one on the left is an urban heat island data presentation tool. The middle one is an application that accompanied a paper on intertidal zones. We call it the mud map. The third one is a surface water app. I'll talk more about that one in just a minute. And then the last one is just a simple time series inspector. And building apps like this is usually just a few more lines of code in your Earth Engine application, but then you've got something that can be deployed both to the web and in some cases directly to a phone. All right, so what is it good for? You've heard kind of how people use it and why we developed it, but what is it good? Why would you want to use it? What is it good at? Essentially, we are built to process things like Landsat images and Sentinel images. That was our genesis, and the vast majority of the work that we put into it is around 2D gridded processing. We're very good at things that are parallelizable because the backend is in fact a giant parallel processing system. That means we're actually bad at things that aren't parallelizable. And anything involving finite neighborhoods is actually pretty easy on Earth Engine. Sorry about that. That tends to look like things like band math, spectral unmixing, texture and smoothing for neighborhoods. We're pretty good at time series analysis, and many of our users use us for some kind of machine learning classification. I'd estimate probably 80% or more of our users ultimately do some kind of classification on their data. The things that we're bad at are things that don't fit well into a functional model, because under the covers, we're basically a functional programming language, but we try to hide that as much as possible because nobody likes functional programming languages. So things that are tough are iteration and recursion and convergence. And that means processes like finite element analysis are almost impossible on us. You might be able to make it work, but you'll have a bad time doing it. And so applications that flow from that are very difficult to do on us are things like hydrologic flow, where a little bit of rain over here, you have to track all the way through maybe an entire continent to see what kind of output happens on the other end. Things like graph theory and networking, where you're not necessarily working on a neighborhood of pixels. You might be working on a neighborhood of features or something like that, but those two areas are just underdeveloped in Earth Engine yet. All right, so normally this is the part of my talk where I would give a bunch of examples, but if you've looked at the schedule, you'll see that right after me come a whole bunch of lightning talks with a whole bunch of examples. So I've pruned this down to an example that I was intimately involved with and an example that I really like to talk about, and I've kind of ignored the others for a minute. This first example is from a paper that I got to be on in 2016, produced with a group at the JRC there in Italy, in Innsbruck. What we did is we took every single Landsat scene, it was about 3 million, and we processed it to detect water or no water. And then we stacked all of those up and we extracted statistics over time. And so this map that you're looking at here is water probability through time. And so the gray areas are places where there was 0% water, and the blue areas are the places where there was 100% water. And then the reds and purples are a scale between 0 and 100%. So in this completely static image, you can actually see down here in the lower right floodplains that are occasionally wet. Maybe there's an annual flood, but then in certain places, water hangs around almost the whole year, but the rest of them dry up. This was a fun project, but it was also the biggest thing we'd ever done in 2016. So it was 3 million Landsat scenes. It was almost 2 petabytes of data. The total computational cost was 1,200 years worth of computation, and the output was 384 layers, one image, one composite image per month for every year for 32 years. We ended up getting a paper in Nature out of that. But that data set is in Earth Engine waiting for people to use it, ready for people to use it. There's also a really nice app that we built as a prototype for Earth Engine apps. So this is the Global Surface Water Explorer. We built this using traditional web development techniques. A web developer, built this, put these elements together exactly like you would expect a web app to be built. And then we used this as the prototype for how do we let users do that without having to do all of this web programming. All right, so my second example is from a project called Disarm, and it's malaria risk mapping. This was with a group at Oxford and the Wellcome Trust, and it's essentially a big classification problem, but it's a really cool one. The idea is to take a bunch of environmental factors like temperature, precipitation, and land use, a bunch of occurrence data, and build a map to identify the risk for malaria. You can't map individual mosquitoes, but you can map the environments in which mosquitoes are likely to breed. And that's what this does. And so it gives you sort of a 6-week warning where to expect malaria outbreaks in the future. The way this works is they take actual occurrence data. They take covariates like elevation here, and then this is a wetness index along with many other covariates. And they put them together into a monthly predictor. And so here's the monthly predictor based on those training data and those covariates. And then over multiple years, they find the areas of highest risk. And with that, we can join that with interventions that have already occurred. And so this map here, the black areas are places where bed nets have already been distributed. So if we zoom in on an area, you can see that portions of this village have been have already had interventions applied to them, and other portions haven't. And so if there's an intervention to come up, you can direct where that should go, so you can apply the limited resources for the risk mitigation. All of this has been wrapped up in an application called Disarm, available that people used on both the web and on phones, and you were able to get timely results of where to apply interventions for minimizing disease. So I like that one a lot, just because it has a very tangible, on the ground output. All right, so where are we at? Our status is that Earth Engine is free for academic and research use. We've currently got more than 300,000 users in 210 countries. The way that you use it is you put together algorithms that we've built, things that already know how to do parallel processing, but you then just compose them together to build the algorithm that you want. We also provide a large quota for users that just for our free users. we found that the free quota is more than enough for most cases, but if you want to do something really big, it may not be enough. And so either for those users, either we support you by giving you a grant for Earth Engine usage, or we've started now allowing for commercial users. That's in a trial phase. There's limited availability with it, but if you don't fit into the academic and research use model, we are starting to make it possible for users that aren't in that group to start using Earth Engine. Almost every time I give this talk, one of the first questions is Earth Engine going to take my stuff? We make it very clear in our terms of service that everything you do on Earth Engine is yours. We don't claim it. We don't take ownership. In many cases, we can't even see it until you want to share it. But we want to make it as easy as possible for you to share, because that's our success model. You build tools and share them with others, and then those people are able to make use of them. All right, this was a challenging talk because I know that right after me there's a bunch of very advanced Earth Engine users, but I also know that there's perhaps in the audience many people that have never even heard of Earth Engine. But for the advanced Earth Engine users that kind of know what I'm talking about already, I wanted to include some information that you might not already know. And so that's the what's new, what's going on in Earth Engine these days. One of the main things that's happened over the past year and a half is that we've started on an integration with the Cloud AI platform. And this gives you access to TensorFlow for things like convolutional neural networks. It's still in its infancy, but it works. And people are using it to great effect already. I work on the classification modules in Earth Engine frequently, and so a lot of the what's new is about stuff I got to work on. And one of them that just came out is the ability to do species modeling with Maxent. If you do species modeling, you're probably very excited about this. If you don't do species modeling, you've probably never heard of Maxent. But it's a new classifier that we've incorporated that the species modeling community uses very frequently. There's a bunch of other additional classifier enhancements, including gradient tree boosts and k-nearest neighbors, and a new ability to output multiple outputs from classifiers. So you can get the probability of each class, or the raw votes of random forest trees, for instance. We've recently started a community contributed tutorial page in our user docs. And as you can see, there's quite a number of those that have already been contributed. We curate these, help clean them up. But some of our users are the foremost experts in the top of their field, and we try to encourage them to put what they know into a tutorial so that you don't have to learn everything they know. You can piggyback on their knowledge and expertise. And then a thing that I'm quite excited about is that we are working on incorporating the JEDI LiDAR data into Earth Engine, and with that, starting to do biomass estimations globally. So if you happen to be in the land cover or greenhouse gas emissions fields, you should find that super exciting. All right, so how does one get started with Earth Engine? It's pretty easy. You go to earthengine.google.com and you sign up. There's a registration page, when registration's instant, and then you're off and running with the freemium quota for Earth Engine. We have an extensive user's guide with tutorials, videos, and API reference. There's on the order of 400 pages in our user's guide, which is both good and bad. There's a lot of docs, but the downside is there's a lot of docs. So plenty there to get into, and a lot of step-by-step tutorials of how to start from nothing and work your way up to being an Earth Engine expert. When you run into trouble, we have an online users group with some 20,000 users in it, and then lots of people seek help and get help using the GIS Stack Exchange group. All right, as I was fearing starting early means that we have even more time for questions, but that's my presentation, and I'm happy to field any questions you might have. Thanks.
Thank you, Noel. Thank you very much for your presentation. I think that we will receive more questions during the day, but for the moment I have some questions now for... can you tell us more or less what is the dimension, the relative dimension, the relative importance? Okay, we have some question also from Sergey. The relative dimension of Google Earth Engine within the big family of Google. If you can something rough idea, let's say.
I'm trying to figure out what scale I might be able to compare it to. Engineering-wise, we're a tiny team. We always have been. Gosh, I don't, that's a tough question. Let me try to answer it by answering a different question. There are now hundreds of teams within Google that rely on Earth Engine on a daily basis to get their work done. So we're just viewed as internal infrastructure by the company, to the point where they're willing to put business critical applications on us. So our company is willing to bank on us as a back-end platform because we've demonstrated 10 years of reliability. I understand that there might be reluctance in other communities, other businesses to do that. And my answer is always the same, which is you can only judge a company or its product based on the track record of that company or product. Google as a company has a pretty bad track record of deprecating products, but on the other hand, Google Reader was not used internally as infrastructure. It was a consumer-facing product. Because we are critical infrastructure for so many projects at Google, I'm very comfortable about our future, and it's just getting better all the time.
Okay, thank you, Noel. I think we have a question from some researcher, from Sergey. Some researcher like me work in R. Does any library work with Google Earth Engine?
The answer is sort of yes, but no. Because Earth Engine is a web service, a REST API, it's possible to use it from any language. That said, it may not be easy to use it from any language. R is a very popular language for data scientists, and there are in fact a couple of libraries to make it easy to use Earth Engine with R. But exactly the same as the Python, you will not be able to use random arbitrary R packages with the petabytes of Earth Engine data. People that use R with Earth Engine typically start with Earth Engine, do things like cloud masking and compositing, and maybe make a temporal time series for a country, and then pull that data into their local R instance and do additional processing with it there, exactly the same as you would with Python. And that works pretty well, I hear. I've only used the R interface once or twice. There are a number of our close partners that have R interfaces built in. One that comes to mind is FAO with their CPL platform. They use both Earth Engine and R somewhat interchangeably on their platform. But like I said, it does involve pulling that data out of Earth Engine to put it into R, a single instance of R. And so you're limited in the amount of data you're going to be able to get into that and the amount of processing that you're going to be able to push through it.
Okay, in the meanwhile, there are some questions arriving. I pass to you, Noel. Where is it possible to take a look at the algorithms written in Google Earth Engine function, how to avoid memory exceed problems analyzing big areas through time by avoiding to rescale pixels? A mix of...
That question is from a Earth Engine user that's been bitten. It is... one of the nice things about Earth Engine is it's very easy to process on petabytes of data, millions of images. One of the downsides of Earth Engine is that it's very easy to process on millions of images and petabytes of data. The way Earth Engine works is it wants to split problems up into small pieces and work on each small piece. But because it's so easy to just bring in a new data set, it's very easy to make each of those pieces enormous. So you might want to process on the entire stack of all Sentinel-2 images. I think that's on the order of 20 million images at this point. It is certainly possible to do that, but if you're not careful, you might end up trying to cram all 20 million images into a single processing unit and therefore run out of memory. So we have in our user's guide some debugging pages on what to do when you hit out of memory problems. That's our best information for a general case. For specific cases, the best option is to just post the problem you're having to our users forum, and then we've got lots and lots of advanced users that like trying to answer those questions to help you out with those. That's about the best I can do in terms of how to avoid those kinds of problems. It is, I will easily concede that it is a bit of a black art trying to handle incredibly large scale computations. Because Earth Engine doesn't work the way most systems work, it's very difficult to conceptualize the flow of data through the system. So it's often the case that you'll try to do something that seems like a normal thing you would do. You might write a for loop to loop through a bunch of images. Earth Engine doesn't work that way, and you're actually making the problem worse rather than making it easier. So our how to avoid user memory limits debugging page is the best place to start, and then for specific problems, ask for help.
Okay, Noel, and another question regarding, this is a question that you probably received many times, regarding the amount of space available in the hard disk of Google platform. So, because I see now that every time that I see a presentation from you is always an increasing amount of petabytes. Is there a limit there? Do you think that you will somehow find a limit there?
There's a diminishing returns limit. Earth Engine exists because we want the world to be able to do sustainable development and manage resources. It is essentially an altruistic endeavor, but there are real costs to running it, and there is certainly a limit to how much value the company perceives for the product versus the return that we see, the improvement in the world that we see from it. And so we hit this constantly with things like the Landsat reprocessing, or when Sentinel-2 gets reprocessed, we're going to see this. But we're hitting it right now with Landsat because they just released Collection 2. They just pushed out 11 petabytes of data on top of the 7 petabytes of Landsat data that already exists. And so if we go and we grab all the Landsat Collection 2 data, we're going to increase the entire size of our catalog by 25%. And that has real costs. Like that's not free. So we have to weigh how valuable is that data set versus how much that's going to cost us. And we make those trade-offs all the time. For some data sets like Landsat, which are fundamental to Earth observation processing, the calculus is very easy. We need to get collection 2. So we need to figure out how to be able to afford getting that data. But there are now, in addition to collection 2, there are now many additional versions of Landsat. There's a harmonized Landsat Sentinel-2 data set, which is now the entire size of Landsat plus the entire size of Sentinel-2. So that's going to be 30 petabytes on its own. There's a different version of harmonized Landsat and Sentinel-2 at the Sentinel-2 scale. And so that's going to be another 30 petabytes. There's an ARD version of data of Landsat, which is another 12 petabytes. And so every one of these, we have to make a trade-off of how much more valuable is that version of the data versus this other version. And we just go through those calculations all the time to try to figure out what's the most important thing to put in the data set or to put into the system. The same thing is true, of course, for algorithms and other backend features. You might find a particular what we call a user journey, a particular path through Earth Engine to be bumpy and difficult. The reason we don't put a lot of resources into solving that particular problem is that if it's possible, then great. If it's not possible, that's maybe a thing that we'll want to work on more than trying to smooth out things that you can do but are just difficult. So where do we put our limited resources? And the amount of resources that we get are proportional to the impacts that we see Earth Engine having in the world. So what that means is publish, make papers, make apps, do as much as you can with Earth Engine and tell people about it. That folds into essentially currency for us to be able to then get more resources to be able to invest into Earth Engine to be able to get these data sets and other engineering efforts.
Okay, Noel. Another question: are you ready for the Landsat 9? I mean, we will have available imagery as soon as they are released, or we can expect some delay between the acquisition from NASA and the availability in Google Earth Engine, or?
That will depend a lot on the Landsat operations team and how careful they are in producing sample data products. If the Landsat 9 data products look exactly like the Landsat 8 data products and come out the same way, then for us, that's just flipping a switch and we'll be able to have those online in a day or two or maybe a week after they come out. But in my experience, that's never actually happened that way. Landsat 9 will be a little different through some aspect of it, and those typically trip us up. I have an interesting anecdote about data sets. Imagine you're a data set provider and you've been churning out data the same way for 2 or 3 years, but then you need to make a change. You need to add some metadata or remove some metadata or change scaling factors, or you make some change to your data set. And once every 3 years, that's not so bad, right? Users should be able to keep up with that. But we have 750 data sets and we're adding more. What that means for us is essentially every single day, some provider changes something about a data set and we have to go fix what we've got. And so we see this mismatch between what we're expecting to get or what we've been expecting to get and what actually happens. And I'm almost certain that the Landsat 9 data will have something that's a little different that we'll have to work through how to deal with versus Landsat 8. So we're excited for it to come out. We're happy to host it when it comes in, but it will probably take us a little bit of time to catch up to whatever new data standard they export their data with.
Okay, we have some more questions here. We have a question regarding, but there are some basic questions maybe we will answer during the course or the workshop we will have in the afternoon for people who who are not experienced yet in using Google Earth Engine. But we have a basic question. Will you launching open source software like QGIS in the future? Is in your plan to have, because you show already an integration between QGIS, are you thinking about a product that is somehow similar to?
Well, I'll try and piece a question out of that. Earth Engine itself is probably never going to be available as open source. And the reason for that is that we're built on top of this giant parallel processing system that is a Google platform. And that is something we won't be able to open source. Everything that happens after the Earth Engine backend is something that we think we can open source. And we often try to. There are most of the code that sits on top of Earth Engine, so the things that people write in the code editor, actually ends up in open source repositories. All of the examples and modules that we produce, those are all open sourced. But the underlying fundamentals of how do we move pixels around, unfortunately, that's based on Google's parallel processing technologies, and we don't have the ability to be able to open source those pieces. So even if Earth Engine was completely open sourced, you wouldn't be able to compile it or run it. And in fact, lots of it might not even make sense because the pieces that it uses are things that are bizarre and weird, but very well developed for parallel processing.
Okay, thank you. We have a more technical questions regarding tiling. How you manage, Google Earth Engine users clearly see that you manage data in tiles, depending of the scale of visualization and so on. Is there, you can explain in a few words how you manage this system of tiling the data in tiles?
Sure, but first I want to point out that our goal is for the tiling to never be something that you have to care about. It's simply the work unit that we use to pass data around. So when we get something like a Landsat image or a Sentinel image, we chop those up into pieces and we store those pieces in our database. But the pieces are chopped up in such a way that they can be reconstituted back into the exact same original data that we got. And we go through to great lengths to try to ensure that the tiling doesn't affect the output results. What this means in practice is that for almost all the operations that Earth Engine allows you to do, tiling is irrelevant. It's just something for us to make it parallelizable. The flip side of that is that there's whole avenues of data processing that don't work in a tiled distributed fashion. There's algorithms that we can't include in Earth Engine because no one has ever invented a distributed version of that algorithm. One that comes to mind is dbScan or like hydrologic flow, right? There's just not good parallel processing versions of these because we can't implement the non-parallel processing version because we would need to load 1 million tiles into one machine, and we just can't do that. So the tiling that we do is supposed to be transparent. There are But it's not, right? We try to make it as transparent as possible, but certainly when you're looking at a map and you zoom out and you're looking at a downsampled version of your data, something had to happen to those tiles to give you a downsampled version. And we document this very carefully in the Earth Engine Users Guide about what we do. But it is important to note that when you're looking at downsampled versions of things, they are in fact downsampled inputs that we're working with and not downsampled outputs.
Okay, Noel, one more. Is it possible to develop directly application for the App Store or only web apps?
For the App Store?
Yeah. This is the exact wording.
That makes sense. I was just trying to make sure that's what it was. Yes, that would be possible. We haven't done anything to make it particularly easy. As I said before, Earth Engine is just a web API. It's a REST API. And most apps that don't run entirely on your phone, they're running against some other REST API out in the world. So it would not be difficult to make an app for a phone, an App Store app for either your iPhone or your Android phone that queried Earth Engine for data. That said, it is not that's not the type of access that we're built for. And in fact, that prospect's a little scary. If you built an iPhone app and 1 million people downloaded it, we'd probably be in trouble, right? We are not geared up for 1 million people to hit the same data set or the same piece of Earth Engine at the same time. In computer programming circles, this is called the Slashdot effect. You make it to the front page of Slashdot or the front page of any newspaper, and 1 million people come and look at your app or your product. And I think we would have some scaling issues with that. But aside from that, it should work, and you should be able to build any number of apps that query the back end for data or for results. One more caveat there, that transmission path, that what we call the wire format of communicating with Earth Engine, isn't particularly well optimized for low bandwidth environments. Our typical users on a desktop with a pretty good internet connection, so we don't go to great efforts to minimize the size or the amount of communications back and forth between our apps and the back end. So it might end up being a bandwidth hog is just where I'm headed with that. But possible, yes.
Okay, Noel, we have a question here in the chat from Luca. Is it possible for a user to request an extension of the memory limits for a specific project?
Unfortunately, no. That's a really common question. And the reason is that Google's compute fleet is made up of a bunch of the cheapest machines we can find. Millions and millions of really small, really cheap machines. And there's a physical limitation on the size of the memory of those machines. It's typically 2 gig. So the maximum amount of data that we can pull into any one machine at a time is something like 2 gig. And if your tiled result needs more than 2 gigs worth of inputs, that's when you hit these memory limits. The out of memory problems are physical limitations that are not quota. You haven't run out of quota. You've hit the end of the machine, right? There's no more data, no more machine to have there. That said, there are some tricks that allow you to do things like using smaller tiles or other optimizations that minimize the amount of data that goes into any piece of the computation. And unfortunately, that's our best answer. There just is no way to get a bigger machine for the processes that we're working with.
Okay, thank you. We have a question regarding hyperspectral imaging. Do you think that the availability of hyperspectral dataset will increase in the future within the dataset available in Google Earth Engine?
Certainly they will increase. The problem is that it's the same problem as we have with Sentinel and Landsat. It's so easy to bring in a whole bunch of data that typically people do. If you have an entire 1024 band hyperspectral image, a thing you might want to do is just get a mean of that. And that seems like an easy process, but that means that every single tile needs to bring in 1,000 bands worth of data. And it's very easy to exceed limits again. So there are a very small number of hyperspectral data sets already in Earth Engine. I'm skeptical here. This is my skeptical face. I'm skeptical about how well those work in the environment we have, just because it's often the case that you're touching every single band and you'll hit memory limits. There is some Avarice data already in Earth Engine. So for the people that use hyperspectral data, you're probably familiar with Avarice. Using that data in Earth Engine is tricky because it isn't already atmospherically processed. And the atmospheric processing does touch every single band. And so getting a single Avarice scene processed to atmospheric clarity using something like dark object subtraction is an expensive operation and usually takes all of the bandwidth, all of the memory room that is available. And so then doing additional processing on top of that becomes problematic. So we're not currently configured well for hyperspectral data. You can make it work, but it isn't necessarily the best time. You won't necessarily have the best time using us to do that.
Okay, thank you. We have another question regarding the development of new machine learning regression algorithm. In addition to the already implemented algorithm there, do you think that you will provide, I see that you presented already a very interesting connection with TensorFlow. Do you see that this area is increasing in the future?
Yeah. So there's good news and bad news on this front, and it totally depends on your point of view. The world is moving more and more towards things like TensorFlow and convolutional neural networks and big AI. CNN's sort of transition from what we call machine learning to AI, or at least how we think of it. The problem with using this advanced technology is that in our case, it's built on top of the cloud AI platform, and that's not free. Using cloud AI platform requires somebody paying for what you're doing. For some of it, we'll pay for it, but if you want to train a giant model using cloud AI platform, typically you end up paying for that. And that makes me sad because it gets right in the way of my mission of trying to solve societal problems, because often the researchers we work with can't figure out a way to pay for that. So I am constantly trying to figure out how to augment our traditional machine learning tools, which are free, with new algorithms and new ways to not have to break out the big guns of something like a convolutional neural network. That's a very long answer to say, file a feature request. If you've got a particular machine learning algorithm that you're interested in, let us know. Just like our data sets, feature requests like that are voted on, and we try to act on the ones that get the most attention, the ones that people want the most. And I really like working on that kind of engineering problem. Those are the ones I really get into. So yeah, let us know what you want, and we'll see what we can do.
Okay, Noel, we have a question regarding desktop requirements. Is there any desktop requirement or browser to run Google Earth Engine?
There are essentially no requirements, but you need some internet. We have people that use us with a pretty crummy internet, so you just need some. I don't want to say the faster the better, but the more stable the better. I have run entire Earth Engine training workshops off of my phone. So that's all the more internet you need, but my phone connection is pretty good, right? I especially here in Europe, I can get consistent internet off of my phone and it works fine. And you need a modern browser. And so if you're using Internet Explorer, you're going to have a hard time. If you're using old versions of Firefox, you're probably going to have a hard time. They will probably work, but there are certain features that may not. So what we recommend is a recent version of Chrome and at least a cell phone's worth of internet. And that's pretty much it. There's not a significant CPU requirement. There's not a high-end display requirement. An iPad with an internet connection should work just fine.
Okay, so one last question from my side, more on the political side, let's say, looking from the European point of view. How do you see the connection, the cooperation between the Copernicus infrastructure, or in general the European Union, let's say, and because, you know, from our personal point of view, we may say we may how to say see that some people in the European Commission or in the European agencies somehow are let's say worried about relying all such relevant spatial research activities of the European scientists relying on a platform that is not from a European. I understand that, I mean, from a researcher point of view, I mean, we are very used to see in a network, so we don't see the problem. But I see that from a political point of view, sometimes we see this kind of, it's not really something that people say directly, but, you know, what is your feeling in this?
Does it matter that I'm in Switzerland? Like, I guess that doesn't quite count as European Union either, but so it doesn't really solve the problem. But I've lived in Switzerland for 5 years now. I came to Switzerland specifically because I wanted to work with Europeans and sort of the European style of research. I found it quite fascinating. And the European Commission commissioning research in Europe fascinated me too. So I wanted to come explore and see. It's quite different than the way research is funded and carried out in the US, and I wanted to come try it out and see how it works out. So I'm familiar with the issues intimately, like deeply familiar with the issues. So I kind of know what you're asking. Relying on a North American company is, or a North American-based company is politically fraught with peril. And as we're designing Earth Engine, we think about things along this line frequently. And so what I mean by that is there is almost nothing Earth Engine does that isn't obvious. We have 1,000 algorithms, but I'm not worried about those algorithms being closed source because what they do is obvious from their name. We have an algorithm that adds 2 images. That's not secret sauce. You can do that in almost any platform with almost any data processing tool. We have an algorithm that does random forest. Same thing. There's lots of random forests. They're essentially interchangeable. There are almost none of these algorithms that we have that do something special. We just have a place that has lots of them and lots of data, and we put them together so that you can use them. Where I'm headed with this is that it is not uncommon that researchers will come to Earth Engine and use us for exploration and discovery. What happens if I put these 2 data sets together with this kind of processing and this kind of processing? That's a question you can answer in minutes and get an approximation, or hours and get a concrete result. How much wheat is there in the Ukraine? Well, that's a thing you can, there's papers published about this. You can grab an existing piece of code, run it, and get an answer in 25 minutes. You don't want to do Ukraine, you want to do Colombia, you change one line, and you can get an answer for Colombia in 25 minutes. So this exploration and discovery and visualization is what we're built for. That's the thing that we excel at and what we encourage people to use us for. We then see a whole class of users that say, thanks, that was great, but now I need to build something real, something I can rely on, something I can own and understand every aspect of. And those users often take what they built in Earth Engine, the obvious bits, move them out of Earth Engine into another tool, which requires retooling, but you've done the hard work, which is the experimentation, and build a Python-based app in Amazon. I hate to say that, but they build it someplace that's not Google, maybe on the DSs, maybe on their own servers. Like lots and lots of our users have their own data centers. They just don't have all the data available, and so they prototype on us. They get to a product that they can publish, and then they want to build a business, and so they'll take that out of Earth Engine and go put it into a commercial environment for them where they can control everything about it, including costs. Because Earth Engine is only just now becoming available for commercial use, this is what people have done for 10 years. And so we've seen people over and over spin a business off out of Earth Engine, and that's how they do it. Now that Earth Engine is becoming commercially available and all of the things that you would expect from some other commercial service are now being folded into the Earth Engine terms of service and service model, maybe you won't need to spin out into something else. Maybe you can still use Earth Engine to do that. But if you want to do it somewhere else, that's fine too. I don't have any particular reason for you to need to stay in Earth Engine. I want you to use Earth Engine so that whatever you develop is then easily shared with other people. That is really the first, second, and third thing I care about, is the ability to reach more people, for you to reach more people as fast as possible. And so if there's other ways for you to do that, that's fine. I care about the impacts, not the tool to get there. Earth Engine is just a vehicle for us to try to have this social impact. How's that?
Yeah. Thank you, Noel. So thank you for your time. Thank you for staying with us, and thank you for the work that you have done. I have to say that personally, you contributed a lot in making reality what I was dreaming when I was a PhD student. Now we can do many things that 20 years ago it was just a dream. So thank you very much. Of course, you are very welcome if you can stay with us. But now I give the floor to the first presentation of the application. So it's the floor is for Giulio. If you are Giulio Castelli, if you are ready.
Yes, can you hear me?
Yes, we can hear you, so the floor is yours.
Okay, so thank you very much, Gerardo, for involving us in this great research unit and also great event. Yeah, also for me, I work in my bachelor and master's with remote sensing, and it's like a dream to have Google Earth Engine now. So really thanks to Dr. Gorelick for this great innovation and for being here with us today. So I'm just going to share my presentation, which is about application of Google Earth Engine for monitoring agroecosystem in data scarce and fragile regions, which is made by me and Professor Elena Bresci. We work in the Department of Agriculture. I am a researcher. And our activity deals mainly with land and water management in fragile agroecosystem arid areas where usually we need remote sensing to fulfill our analysis. So basically, we work in data scarce regions where we have limited availability of ground data. Often we have discontinuity of time series, and this implies often a lack of environmental monitoring procedures, the decision support system for environmental management, and moreover, a long-term monitoring of land and water management. At the same time, when we work in these environments, we have very much exposed to vulnerability to extreme events and climate change in general. At the same time, we need to test innovative solutions against climate change, and we need to generate data for environmental land and water management. So we have two bad things. We don't have data, but at the same time, we need this data to fight against climate change. And how does cloud-based spatial computing can help? First of all, it can help in expanding the scale from field-side experiment to regional analysis. So we can make one experiment and then we can generalize the experiment with remote sensing. Then we can extend our experiment in time, so we can make maybe a short experiment to validate remote sensing methodology. Then we can use remote sensing for a longer time series. And then, again, cloud-based spatial computing, it has the Google Earth Engine, can provide innovative data and information for management. So I'm going to show quickly two case studies that we developed in these years, where we just imply the functionalities of Google Earth Engine to do these things. So the first case study was for the monitoring of water harvesting and soil conservation system in Tunisia, where there is a traditional water harvesting technique that is called Jessur. It's a water management technique made by a terrace in a dry riverbed. So these technologies are working very well. They are used by smallholder farmers, and we would really love to assess their impact with an evidence-based procedure. So what we did an analysis of soil moisture at plot scale in remote smallholder farm areas. Then with Google Earth Engine, we correlate with soil moisture analysis with an index that is called normalized different infrared index and also normalized difference water index. And we found that this index was really well correlated with surface soil moisture in these environments. So what happened is that we managed to evaluate over a longer time series and a larger area that actually the gesture system can really retain much higher soil moisture even in the dry season with respect to the traditional growing system of olive trees, which are key cultivation for Tunisia. And this was a result because it showed with a scientific application that the large scale application of this water harvesting technique can be actually used for buffering the effect of climate change on water resources in Tunisia. So this is the paper that we made, and I'm very happy that we managed to do this with Tunisian colleagues. Also, I mean, Google Earth Engine does not involve a very high computational requirement. You don't need to download hundreds of remote sensing images, so it helps also in this way for working in remote areas and maybe where the computational capabilities are not that much, because basically you do computation thanks to Google servers. So the second case study that I want to show allows to understand how also Google Earth Engine can allow to merge and blend different types of data. And it's about the analysis that we made to understand if the retention of water in the soil could allow mesoclimate mitigation or regulation in dry climates. I've just put a very, scientific slide about the process. So the idea is that if we are in a dry area and if we have soil moisture, even if we have a lot of solar radiation, this energy is depleted to convert the soil moisture in water vapor by evapotranspiration. So in this way, you deplete a lot of energy for changing the physical status of water, and this energy, on the other hand, is not used for heating the air. So this means that if you have soil moisture, you can have a cooler environment. Is the same thing that you can observe when you have maybe water nebulizer in a bar. So they spray water because thanks to the water evaporation, you have a cooling effect. So what we did was using Google Earth Engine to evaluate if this effect could be visible at a catchment scale in an arid area. So what we did was to imply Google Earth Engine to derive an index, a synthetic index of water conservation that was basically, again, this index normalized different infrared index, which is correlated to the root zone soil moisture, and the rainfall of the rainy season. Of course, we have taken both the index and then the rainfall of the rainy season by Google Earth Engine, because Google Earth Engine has a very good database for rainfall. That is a dataset called CHIRPS. And we also create a synthetic index for temperature, which was the ratio, between the land surface temperature calculated by MODIS satellite, again from Google Earth Engine, divided by the temperature at 850 hectopascal. This last one we didn't take from Earth Engine, but directly from the ERA interim dataset. So what we did was basically to check if at the catchment scale in a semi-arid area, the implementation of this water harvesting, water conservation, and soil conservation techniques could retain a sufficient amount of water in the soil to have a cooling effect. And we did this by comparing the water conservation index and the temperature index. So what we found, and again, thanks to Google Earth Engine, it was that after the implementation of these water conservation techniques, namely terraces, infiltration trenches, reforestation techniques, this watershed, this river basin located in the north of Ethiopia, had an increase of water conservation, a decrease in the temperature index, and a decrease in the land surface temperature. You can see it clearly from this graph. So you can see here that before the implementation that was made in 2008, all the points representing the condition of the catchment were with high temperature index and low conservation index. While after the implementation of these technologies, after 2008, we have the catchment in a status with lower temperatures and higher soil and water conservation. So what happened? It happened that after the implementation of water conservation in the catchment, we had more water in the soil and less temperature. So this was, yes?
Giulio, if you can move to the
yes, so this is the paper, and I finished. So these are some references and our comments. Thank you very much.
Thank you very much, Giulio, for staying also in time. For the moment, we don't have questions, so I move to the next presenter here, to Francesca. Please, Francesca.
Hi, thank you, and for all the presenters that are here. I am also an organizer, so thank you, all of you. I am Francesca Giannetti, and I work at the Department of Agriculture in the Laboratory of Forest Geomatics. And we are involved with more or less in the analysis of forest ecosystem, especially in the Mediterranean area. Here in my presentation, I will show you just some example on how we are going to use Google Earth Engine to monitor natural disturbance, especially Mediterranean forest. We use to monitor Mediterranean disturbance, especially satellite images. In the last year, we use Sentinel-2 data, since the high temporal and spatial resolution of these types of data. Natural disturbances are really important in the Mediterranean region, since forests in that area are a great ecosystem where there are a variety of species that have a really important aspect in the conservation of biodiversity. We know also that Mediterranean area is also one of the most ecosystem or regions affected by climate change. In fact, if we look, for example, in the graph of the temperature, we see that the increasing of temperature in Mediterranean region is higher than the one registered in other ecosystem region or bioregions. In Mediterranean area, we have we can divide the natural disturbance in 4 categories: forest fire, drought events, insect outbreaks, and windstorm and stronger rainfall. These natural disturbances affect the forest ecosystem and produce different disturbances. Forest fire, for example, destroyed every year 6,000 of forest hectares in Mediterranean countries, and in the last year we registered, for example, in Portugal, Spain, and Greece, a very huge forest fire where people died and so the increasing also of the strong forest fire. Drought events affect trees mortalities, so the mortality of trees is increasing, especially in some tree species. For example, Quercus, we register a decline of Quercus oak, oak species in Mediterranean area, and this water stress due to drought increase also the insect outbreaks. So some forests are destroyed, as we can register, for example, in Canada, where huge insect outbreaks were. Also, windstorm and rainfall, strong events, impact on the stability and conservation of forests in Mediterranean area due to the increasing on temperature and the increasing on cyclone in that area. How we can use Sentinel-2 data and Google Earth Engine to monitor and to quantify the state of health and the degradation that we can have after a forest natural forest disturbances. So the disturbance in natural disturbance always exist. However, the intensity of the outer events and also the intensity of these and the number of these event increase. So we need to monitor not only to map where the forest disturbance is, but also how is the evolution of forest system after an event. Here there is a simple example of one forest fire that was here in Tuscany. We were able just with a classical change detection approach to monitor the area of this forest fire disturbance. However, thanks to the possibility to extract from Google Earth Engine the trajectories of each of these pixels, we are also able to calculate some metric to understand the regrowth of forest system, and also if there is a degradation of this forest, or this forest will return naturally. So now we are, here there is a set of metrics that were proposed by White for Canada, and we are working to monitor the regeneration of this forest fire using this approach, in order to create some forest activities to restore this environment. Another example, here there is, for example, the amount of pixels that return to the same level of photosynthetic activities. And we can also use this multi-temporal approach to detect, for example, windstorm. Here we use two continuous change detection algorithms that were developed for Landsat time series, where we can detect windstorm damage area to have the possibility to estimate with a probability-based stratified estimation the area destroyed by this forest, and also use this map to monitor the evolution of windstorm. With the same approach, we can also monitor, for example, the insect outbreak. Here is a pine forest in the coast in Tuscany, where we can see the evolution of insect outbreaks looking at the time series of Sentinel-2 data. Why this is really important? Because time series imagery and the possibility to use Google Earth Engine to process this data is completely changed the way to map and also to monitor the effect of natural disturbance in Mediterranean forests, thanks also to the spatial scale of Sentinel-2 data that have 10-meter resolution. The use of Google Earth Engine has made possible to process a large amount of remote sensing data easily, also from my phone, so it's not important to have a big computer to process the data and to give the possibility to extract information, and also have the possibility to calculate many recovery metrics that can be used to monitor the effect of natural disturbance that are essentially to promptly propose mitigation action, especially in the restoration of forest ecosystem. This is just some example, and thank you for your attention.
Okay. Thank you very much, Francesca. Now we move directly to the next presenter, Saverio, again from the University of Florence. Please, Saverio.
Hi all. I am Saverio Francini, a PhD student from the University of Viterbo and the University of Molise. And I work in the University of Florence, that is the university that has organized this event together with the Copernicus Academy. First of all, I want to thank Noel Gorelik for his participation. Thank you very much. Okay. I'll talk you about forest disturbance mapping and area estimation using Google Earth Engine. So, forest disturbances can be mapped using remote sensing images, as you can see also from the GIF in the background. So you are looking at an MBR time series calculated using Google Earth Engine and Landsat images. So forest disturbances can be mapped using remote sensing images, and for this reason a lot of forest disturbances algorithms exist and are also available on Google Earth Engine. So first of all, we tested different algorithms in our region, so in Tuscany, where the majority of forest disturbances or forest harvestings are in Coppice Forest. So we found that forest disturbances in Coppice Forest are characterized by a very rapid spectral recovery, and for this reason algorithms developed for different ecosystems do not work properly. So we developed another approach. The name of this approach is 3i3D, and it was more precise and had a greater recall, F1 score, and Matthew correlation coefficient compared with other algorithms. On the other hand, we found that some omission error persists also in this map. This is due to the variability in natural and anthropic phenomena that occur in forests. For this reason, it is important to remember that forest disturbances should not be used directly to obtain area estimates. Meanwhile, forest disturbances are a great tool to select samples and to calculate area estimates using reference samples or true data. Here we calculated the forest disturbance areas in Tuscany, or in this study area, using a reference sample acquired for 28 cells among 100. And we found that the estimates had a very small standard error, even if using not very precise forest mask, at least in our ecosystem, like the global forest change map. So the method worked well, and for this reason we decided, of course, to implement the method on Google Earth Engine, and we are working on a paper about this. Using Google Earth Engine, we were able to map forest disturbances in the whole Italy, and to do it, we processed about 18,000 Sentinel-2 images. Doing something like this before Google Earth Engine was something nearly impossible, but with Google Earth Engine, actually, it was quite simple. We had just to port our code into JavaScript, and then the game is done. Here, we used a different approach to obtain area estimates. So we select a sample, selecting a lot of points in the boundaries of forest disturbances, because we found that most of errors occurs in boundaries of forest disturbances, and increasing the sampling intensity in that area, we were able to decrease the standard error. This is the formulas we use to obtain the the estimate. And here we have the results. So we estimated the forest disturbance area and the clear-cut area and the fire and wind damage area. The most important thing is that we were able, using this statistical procedure, also to estimate the 95 confidence interval of this value. So we are confident about these results. On the other hand, we have to say that these disturbances are forest disturbances that can be visualized and that are visible using photo interpretation, using remote sensing images or high resolution images. Yeah, this is the 3i3D Google Earth Engine user interface we implemented. Another advantage of Google Earth Engine, like as Noel Gorelick said, is that it allows to share results with other researchers and also to construct application like this one. In this way, different users can test different parameters and try to calibrate the forest disturbance map in order to be as much as possible precise in his study area. Then it is possible to download outputs, Sentinel-2 cloud-free composites, and so on. This afternoon at 2:30, we'll try to construct a very simple application like this one, and I hope that you'll enjoy it. Thank you very much for your attention.
Okay, thank you, Saverio. Okay, here we are. Now it's time for a coffee break. So we will start again following our program at 11:40. Okay, so in 13 minutes. So I hope to find you again here at the end of the coffee break. I will share the screen just to remember that you can contact us through the mobile phone, and see you in 12 minutes. Giovanni, the floor is yours.
Can you see the screen? The presentation?
Yes, we can.
Okay. So, good morning, everybody, and thanks for the invitation to share with you the study entitled Big Data Analytics for Mapping Forest Vulnerability to Climate-Driven Disturbances. As also previous colleagues have pointed out, the topic is relevant and under the spotlight given the recent rise in forest disturbances across the globe. Just let's think about the recent fires in Australia last year, or the large insect outbreaks in North America and Eastern Europe as well. Forests cover about 33% of the European land and provide a set of valuable ecosystem services for human well-being and climate regulation. However, they are also vulnerable systems to sudden climate changes and natural disturbances, such as forest fires, insect outbreaks, and wind throws that can affect seriously the provision of these important ecosystem services. Understanding and quantifying the vulnerability of forests to natural disturbances is fundamental in order to develop appropriate adaptation measures to face with climate changes. And this is particularly important in view of the expected intensification of natural disturbances in the near future, as we can see in the panel on the right, where we see an estimate of the projections of the impact of forest fires, bark beetles, and wind in red, green, and brown, respectively, for the European forest under a business as usual scenario. However, quantifying the vulnerability of forests to natural disturbances is still challenging particularly over large scales, due to our incomplete understanding of the underlying ecological processes and the lack of a consistent and systematic monitoring systems of natural disturbances. On the other hand, there is an emerging number of new tools and products that could provide important new insight and advance our understanding of the dynamics of forest disturbances. And in this study, we tried to fill these the aforementioned gaps and by integrating machine learning methods with satellite data and cloud computing platforms in order to investigate the vulnerability of European forests to fires, wind throws, and insect outbreaks over the last 4 decades in Europe. So we built our methodological framework expressing the relative biomass loss due to a given disturbance, our response variable, as a function of multiple potential predictors. Here C1, CH, S1, SK. Here the models linking the response variable to the predictors is a random forest regression model developed differently for different disturbances and different plant functional types. The response variable, so the relative biomass loss, was derived by integrating high-resolution biomass dynamics and disturbance databases. So the biomass dynamics were obtained by combining global forest change maps and global biomass products, while we use state-of-the-art, spatially explicit collection of disturbance records with respect to forest fires, insect outbreaks, and wind throws. Then we collected a large number of potential predictors, including climate features and forest and landscape metrics retrieved from satellite data and reanalysis data. So, and basically we extracted all this information by the use of the Google Earth Engine platform. We developed our model and tested across a number of observations. And then we apply this model to reconstruct in space and time the vulnerability, expressing here the relative biomass loss, the potential relative biomass loss. In this figure, you see an example for fires. On the left, the average vulnerability of forests to fires. And on the right, we have the local sensitivity, so expressing the marginal contribution that each category plays in driving the vulnerability. So the climate component, the forest component, and the landscape component in red, green, and blue respectively. And the same was replicated for the other 2 natural disturbances considered in this study, so wind throws and insect outbreaks. You can clearly see that the spatial variability of the vulnerability on the left panels is largely dependent on, obviously, on the natural disturbance itself, but also on the local environmental conditions. We estimated about 60% of the European biomass could be potentially vulnerable to natural disturbances. And interestingly, we found that climate and forest predictors play a dominant role in affecting the vulnerability, and this opened an important debate about the role of forest management in reducing the vulnerability and thus increasing ultimately the resilience of these important systems for European citizens. When we look at the evolution in time of the vulnerability, here we see the time series of the vulnerability of forests to fires on the left, aggregated at Europe level, while on the right we see the spatial map of the pixel scale long-term trends, while below the map we have the area fraction where each of the climate drivers is the dominant. And this was performed by an ensemble of factorial simulations in order to detect what were the key drivers of this temporal evolution. The same was done for winters and insect outbreaks. From this figure, we can clearly see again that for the vulnerability to fires and to winters did not change substantially over the last 4 decades, at least when aggregated at Europe level. While in the case of insect outbreaks, we clearly see an important and significant increase in vulnerability of forests, particularly in the northern regions of Europe. And interestingly, we found that this rise in vulnerability started around the year 2000, were corresponding to an increase in temperature of about 0.5 degrees compared to the temperature in the 90s. And this may suggest that around the year 2000, we may have reached a tipping point where further increase in temperature may have led to a reduction of the natural plant defense mechanisms, ultimately leading to a reduction in vulnerability. When we try to integrate this information in a unique indicator here called overall vulnerability index, where we try to integrate the vulnerability to multiple natural disturbances, we found that the most fragile ecosystems are those located at the border of the climate envelope, as you can see in panel E, that corresponds to the region of the northern of Europe, in particular the Scandinavian Peninsula and eastern Russia, and to some extent also to the Iberian Peninsula and the Alps. And these regions basically correspond to forest areas that present an average high vulnerability, but also experienced a progressive high trends in vulnerability. Okay, here are some take-home messages of my brief presentation. Almost 60% of the European forest biomass is potentially vulnerable when impacted by winters, fires, and insect outbreaks, or a combination of these three disturbances that are the major ones for European forests. Due to a rapid warming, vulnerability to insect outbreaks has grown in the past decades, particularly in the north of Europe. And this is also confirmed by recent large insect outbreaks occurred in the eastern of Europe in particular. And the combination of climate and forest structural properties largely control forest vulnerability to these natural disturbances, and these open new opportunities for forest management strategies. So these results and more details have been published in our recent paper in Nature Communication. You can find more details in this paper. And okay, thank you very much for your attention.
Okay, thank you very much, Giovanni. Thank you for staying in your time slot. We don't have very much time now for questions, but maybe we will have at the end of the session. So I give immediately the floor to Ceccherini.
Okay, good morning.
Good morning.
Can you hear?
Yes, we can hear you very well.
Can you see the presentation? Okay. Good morning, Guido Ceccherini. I'm working at the Joint Research Center at the European Commission with Giovanni Forzieri. And thanks Gerardo, thanks Costanza for organizing this workshop, and thanks Noel for giving us Google Earth Engine, this fantastic tool I'm working with in the last 5 years. Today I'm presenting what I've done with my colleagues on European forestry using Google Earth Engine. So we can start with forests that are providing resistant services that are critical to society, from climate mitigation to water regulation and supply. Forests are an important carbon sink, and their protection and their management is key for European Green Deal and to become the first carbon neutral continent by 2050. So given the fundamental relevance of forestry, we need timely, accurate, and robust monitoring of forest harvest. We need to know forestry and its spatial patterns and temporal trends. only in this way can inform and correctly manage and optimize this resource. However, monitoring forestry is still largely based on national forest inventories that are not providing detailed spatial information and timely updates. This means that sometimes we have information on forestry scattered both in space and in time. It's aggregated at coarse spatial level, and sometimes it's difficult to find near real-time information. To have an idea, also in Europe, almost 13% of the harvested forest biomass is not accounted for in official statistics, and it is confounding a lot for the optimization and the management of this resource. But nowadays, we can use the high-resolution satellite that we are flooded with, and the cloud computing platforms such as Google Earth Engine. And in the study I'm presenting, we have combined Landsat time series and Google Earth Engine to map and have an area estimate of change in forest cover across Europe from 2004 to 2018. To do so, we have mainly used the Global Forest Change Dataset. It's a dataset published by Hansen and at the University of Maryland, and it mainly consists of what we have used 2 layers. The first layer is the tree canopy cover for the year 2000. So it's a global map expresses its percentage of trees for the year 2000. The second layer is the year of forest cover loss. So we know for each single pixel at global level when we have a complete removal of tree cover canopy. But however, what we get from remote sensing and in Google Earth Engine is the tree cover fraction, so how many trees are present per pixel. What defines a forest instead is a minimum tree cover canopy, and at European level there is not a common definition of forest for each country in terms of minimum tree cover coverage. Each country adopted a different tree cover threshold that fits better the national circumstances. So the first thing we had to do was to create a methodology to convert tree cover to forest cover. And for each country, we found the tree cover threshold that is minimizing the difference between national forest statistics and remote sensing. In this figure on the left, you can see with different colors ranging from yellow to blue, the optimal tree cover threshold needed to define a forest that minimizes difference between the area declared by national forest inventories and declared to FAUSTAT, and what we found with remote sensing. You see in yellow, and labels indicate the percentage error between the two estimates, and we can see that in yellow there are Spain and countries in the north, while temperate forest in Central Europe has a higher thresholds, higher optimal thresholds. But since we get from satellites, it's a forest loss that can be due to forest harvest, so from natural management or to natural disturbances. And we want to filter out from our analysis what are fires and measure windrows. Regarding fires, we have the Joint Research Center Forest Fires Information System. So we have daily polygons that are supervised on daily basis. So we are quite confident that we can mask out and we know the whereabouts of the measured fires. Regarding windstorm, we did the hypothesis that measured windstorm are causing larger losses than those that can generally caused by forest management. So we regridded with Google Earth Engine at the 20 kilometer scale, and what is an outlier in the forest loss time series is considered a windrow. In blue, in this figure, you can see the measured patterns of windrow found by our crude and rough algorithm, but that show a good match of what we found of the few records you can find in literature of records of measured windstorm in Europe. For instance, this one in France, the one in Germany, Godrum in Denmark. So after filtering out, once we found the optimal tree cover to define a forest, once you filter out natural disturbances from fires and wintro, we can get the European forest harvest. The figure on the left shows the percentage harvested forest per year. The pixel in yellow are those where the forest loss is greater than 2%. As you can see from this time series, there are no particular spatial patterns, especially in magnitude, until 2015. Then, after 2016 onwards, there is an abrupt change, especially in northern and Baltic countries and in the Iberian Peninsula. And with Sweden and Finland, that accounts for more than 50% of the abrupt increase in forest harvest. We also try to address which forests are facing the largest change in harvest. And here in this figure, you can see the mean harvested area for 5 biomass classes.
Guido, sorry if I interrupt you, because I think that we lag your presentation in the sense that we are still watching the natural disturbances figure, page 10. Are you still at page 10?
No, I'm page 15.
Yes, in fact. So maybe you can interrupt the sharing of the screen, and we were able to follow you, but not seeing the. Okay, now you can restart the sharing.
Sorry for. Okay.
No, it's not your fault. I mean.
Okay, can you see slide 12?
Yes, 12. It's okay.
Okay,
thank you.
This was the figure where I'm showing the abrupt increase in forest harvest and the spatial patterns that are quite clear, especially after 2016. And here the national share of the national contribution for this increase of forest harvest. Then, since I think I'm running out of time because the presentation is going to end, there are other slides that I can skip, and the take-home message is that we are flooded with big data and with remote sensing data, and that has a great potential to enhance EU forest monitoring. It's important to have this big data platform such as Google Earth Engine or also the DIAS at the EU level that can improve the implementation of the bioeconomy strategy under the EU Green Deal. And it's important to have this data because it's transparent, it's consistent, and you can share with other users and with other university and research institutes. And with the future integration with Copernicus, so having Sentinel-1, Sentinel-2, and Lancet integration, we can, I think, we should lead to an improvement of at least a factor 9 in the forest loss detection. Thanks for the time and for your attention.
Okay, thank you very much, Guido. We do not have very much time, but I think that at least one question or comment at least is requested, because you know that your paper stimulated the discussion in the scientific community around Europe for this abrupt change, and there is quite a consistent group, let's say, of scientists who are somehow criticizing the way these results are interpreted, in the sense that we know that the Hansen data set may have some inconsistencies in the data and the methods that the data are elaborated. Now we don't have time for going in much details. Just to say that if you are considering for the future the Hansen dataset as a main reference dataset for clear cutting, or in general for monitoring disturbances in European forests.
Okay, thanks, Gerardo. We know that there is a heated discussion behind this paper, and but I think it's important that science is going in this direction. So I think it's important to have some maps that are not also leading for stratified sampling, but also to do trying to do some area estimation to maybe to complement with verification and sample-based estimates. Regarding your question, I will not use Hansen in the future. I hope that it will be, as even a European contributor, there will be Sentinel-1, Sentinel-2, DIAS, and good Copernicus product that can be used on annual basis to map using the consistent data set forest loss. So we know that we can combine, there is Sentinel-1, you can do coherence, that's still not done with Google Earth Engine, I think because it's because of the cost behind. And you can use Sentinel-2 and then on another level produce a decent product. So it's you can use also DIAS to this end. But and regarding the Hansen dataset, we can say that we were not aware of this undocumented change after 2015. You correctly note, because there is a discussion and there is matters arising that will clarify the position that of the inconsistency in the Hansen dataset after 2015, and we did an additional validation that is confirming the direction. It's instead of 43, it's 35%. And there are future activities also to use. There are Olofsson, a professor in Boston University, using buffers to reduce the uncertainty. We are trying to do future activity to do a better estimation, but we are quite happy of the discussion was started. Also yesterday at the European level, we saw an article regarding not only the common agriculture policy, but there is forest agriculture policy. So it's an interesting field, and this is the future. Thanks.
Thank you very much, Guido. I think that we can stay in touch in this. I think that we studied quite well the Hansen data for Italy, and at the end, as you can see from the presentation of Saverio and Francesca, and that we prefer to develop our own methods because we found a lot of inconsistencies in Italy, but Italy was probably a special case. Okay, anyhow, thank you very much again, Guido. Now the floor for Joan Doblas. Hello.
Hi.
Hi, Joan.
How are you seeing me? Are you hearing me?
Yes, we can hear you. You can share your screen.
Okay, I will share my screen right now. Yes, let me know if you are seeing the first slide.
It's okay.
Okay.
You can
okay,
start.
So good morning, everyone. From Brazil, I am Juan Dobles. I am a PhD candidate at the INPE, which is the research, the special research agency of the government of the state. I will present one of these cases where a research became a operational system. In this case, is monitoring a forest deforestation system, which I am developing right now in an operational basis. So the first question is, why a new monitoring system? As you know, there are many monitoring systems on the tropics. One of them is running by the INPE, my institution, but they are all based in optical data, And as you know, in the tropics, during the rainy season, the optical sensors, they are blind. This is a map of the blindness of the optical systems on the Brazilian Amazon. As you know, as you see, many places which register deforestation, we have 5, 6 until 10 months of cloud cover. That's why we think of developing a system of detecting deforestation with using SAR images, which are not covered by clouds, as you know. The literature, that's where my PhD research begins. In the literature, you see that consistently deforestation causes a decrease on the signal of the radar sensors. We can see it easily by choosing images from radar on deforested areas. This is the difference. And the time series, they are also very clear. So we say, why not try to detect deforestation using Sentinel-1 series, as they are freely available from the ESA and available as well on the Earth Engine platform. So my research sample, random, I choose some thousands of points, random points of deforested areas and forest areas, and I try to detect. I applied several models, several algorithms to detect deforestation on an automatic fashion. And I was quite surprised because the accuracy, the figures of accuracy were quite high. The best method reached almost 96% of accuracy with a very low alarm rate, the false alarm rate. That means that we were ready to be operational. At this point, I was hired by the INPE to develop an operational method after the publication of this paper. So we were assured from a theoretical point of view that the detection of deforestation with radar was possible. So we jumped to the personalization, to a first phase of operationalization, using a workflow where we filtered the time series, and then we produced deforested pixel images, which were vectorized. All of that happened in Earth Engine. We use a Python implementation of Earth Engine, the Python API, to implement this workflow, which treats every day. There's a computer that wakes up here in Brazil, look for new images and process these new images over our area of interest, and then produce a shapefile with the deforestation, the deforested areas. This shapefile is sent to the enforcement teams in the field, which will try to deter this deforestation focus. So this began last year. Until now, we have produced approximately 50,000 polygons of deforestation over these 5 areas. This is our first phase of implementation of this system. And what the results, they are very, very interesting. One of the results is that there is deforestation during the rainy season. This is the number of deforestation polygons during the month of October, which is a cloudy month in almost all the Amazonia. So you see that deforestation doesn't stop during the onset of the rainy season, and during this time of the year, the optical sensors, they are almost blind. So this is quite important for the operationalization of deforestation fight. After that, we do a field validation campaign. We took an helicopter from the enforcement teams, and we flew over 100 points almost all of them were real deforestation. One of them, I guess, was a burned area, not a deforested area, but the rest were the real deforestation. And as we use very fresh polygons, we were able to see deforestation almost occurring. This is a photo of our verification routines. There were people deforesting at the very moment we threw the polygons. So now we are in a very exciting moment right now, because we are trying to extend this system to the whole Amazonia. This is a big game, I will say, because we were increased by tenfold our area of monitoring. We are monitoring these 5 areas, and now we will monitor all the Amazon biome. That means 4 million, more than 4 million square kilometers. There's an average of 30 new images, radar images every day that we need to process, and to mask, to vectorize is a very intensive task that we are trying to do, but now is working. Those are the polygons, the heat map of deforestation polygons for the month of March, and the results are pretty interesting, and we are hoping to become operational the whole Amazonia next month. I hope this month even. What are our DeFis and what are our way forward? We have problems with clouds, with convection cells. You know, these very, very heavy storms, and these storms will block the radar signal. And as you see in this image, these can be interpreted as a deforestation, as a deforested area, but it's a cloud. It's actually, this is the record of precipitation. Here you have a spike. So this is something like a cyclone. It's a very, very heavy windstorm that that decreases the radar signal and can fake a deforestation. That's a DeFi that we need to deal with. And also we need to integrate the Sentinel-1B images that now are becoming frequent in the Brazilian Amazon. Until now, we have only covered by the Sentinel-1A, and now we are being covered by the Sentinel-1B that will speed up our detections greatly, and we need to do that. We have some confusion with heavily burning areas, with heavily burned areas. We need to resolve that, but we are trying to do that. And that's all. I thank you very much for the opportunity, and I'm ready to do the questions.
Thank you very much, Juan. Very nice and interesting presentation. Thank you for bringing us back to the radar. Otherwise, we are always focused on optical in this morning. So, thank you very much. We don't have very much time. Maybe I don't have for the moment questions regarding this specific presentation. So I will move to the. If you can, please stop the sharing. Thank you, Juan. Thank you very much. So now I give the floor to Luca Salerno.
Actually, I will start the presentation.
Melissa, sorry, it's your turn.
Yes.
Okay, sorry. The floor is yours, Melissa.
Okay, 1 second. Okay. Can you see my screen?
Yes, we can.
Okay. And this presentation will be split between me and my colleague Luca Salerno. as we are both a PhD student at Politecnico di Torino under the supervision of Professor Carlo Camporeale. Working with Google Earth Engine means for us the possibility to map and monitor vegetation dynamics over remote and poor accessible areas, such as the tropical floodplains, and large study cases, such as continental shorelines. Besides, it means to get information on vegetation status, carbon accounting, and vegetation cover, which are fundamental input data for ecomorphodynamic models. The first application we show today concerns the study of coastal dune vegetation. We formulated a model that describes the behavior of vegetation cover in relation to external stochastic, that means random, forcing, mainly consisting of sea level fluctuations and wind. The model is basically a system of stochastic differential equations and requires to be numerically solved, but it can be simplified to obtain an analytic solution that provides the probability density function of vegetation cover at every location. This means that if we apply this solution to a simple beach, the model gives the extent of the sandy area and the statistical features of the grassy area just behind the beach, offering important information for coastal management and restoration planning. The model requires some physical input data, such as time series for wind, waves, and tides, and these data are available on global datasets. However, it also requires some biological parameters to work, namely the carrying capacity and a couple of decay rates. These fundamental parameters can be defined by calibration, but the calibration needs the prior knowledge of the model's outcome for some training areas, namely the beach width and the statistics of the cover. Thus, we decided to use Google Earth Engine to retrieve this benchmark data. In this case, we used the Python API to integrate the Google Earth Engine optimized functions with external algorithms. We first imported the global shorelines provided by OpenStreetMap, and we drew perpendicular equidistant transects along them. We then selected the transects according to the areas with low erosion or accretion rate, and we filter out all those areas that are altered by anthropic pressure by superposing the largest settlements of the JRC human settlement layer. We then define a set of areas of interest around the remaining transects and looped over them. For each areas of interest, we retrieved Sentinel-2 images from 2017 to now. We firstly selected only the images with cloud cover lower than 10%, and then we worked on bitmasks to operate a per pixel selection of high quality, cloud, snow, and shadow-free pixels. We added to each image a set of spectral indices, and we classified the images thanks to a training set of over 4,000 worldwide points. The SendC interface was further refined by applying an Otsu thresholding to the NDWI band to better mask water. The obtained classified image was then used to compute the extent of the sandy areas along the transects and provide the median beach width. Besides, we apply spectral unmixing to the grassy area, and we obtain vegetation cover and compute the statistics necessary for our model calibration. Here are some examples of the algorithm's output. This sequence shows the selection of the largest urban agglomerates from the global human settlement layer of JRC. While here, we show algorithm's output in terms of image classification and beach width computation. For instance, in the right panel, you can see the OpenStreetMap derived transects that are cut just over the sand before the width computation.
Hi everyone. The second application which we see today focuses on the capability of rivers to foster carbon sequestration through a physically based ecomorphological approach. Rivers represent delicate systems which exhibit a plethora of processes from geomorphology, ecology, hydraulics engineering, and social sciences. Inland waters play a key role in the carbon cycle, and in the last decades, rivers are no longer seen as a passive pipe that transport carbon from land to the ocean, but as an active component of the global carbon cycle that store terrestrially derived carbon in sediment and lose CO2 as emission in the atmosphere. Through the analysis of satellite data, we investigated a new highly efficient carbon pumping mechanism of riverine systems that we call geomorphic carbon pumping, GCP. In such a mechanism, carbon was exported along the river system from the riparian corridors as large woody debris recruited for uprooting or bank erosion during flooding. Furthermore, CO2 sequestration is promoted by vegetation encroachment with further primary production over the new bare bars near the inner banks. The GCP computation was developed in Earth code editor by using JavaScript API. We focused our attention on the natural large tropical rivers wherein the vegetation and river dynamics are not influenced by anthropological activities. Therefore, 200 free-flowing rivers with the river width greater than 200 meters among South America, tropical Africa, and Asia were selected and divided into regions of interest characterized by homogeneous morphological behavior. For each region of interest, the GCP was assessed by using two global datasets. The first one provided the vegetation cover loss due to river geomorphic activities between 2000 and 2019. It was obtained through a filtering process of another dataset developed by Hansen about global forest change. The filtering process allows us to remove all the main non-river related causes of forest loss, such as wildfire, deforestation, or anthropic-induced land cover changes, and so on. The second dataset instead reported the carbon density of each plot of the forest loss. Therefore, GCP was computed as the product between the Hive river-driven forest loss plot and the carbon density in the same plot. Here we can see some fundamental results of analysis across the tropics. Each circle represents a region of interest, and the circle size refers to GCP of region of interest, while the color refers to GCP per unit area. We can see that there are some rivers defined by us big sequestrator, characterized by a very large value of GCP. And in particular, half of the total carbon sequestration is due to 10 of such big sequestrators, each providing a carbon pump exceeding 119 gigagram of carbon per year. We estimated, extending the previous analysis to whole tropical river with stellar order than 4, that geomorphic carbon pumping amounts to 100 million tons of carbon per year, or 0.1 petagram of carbon per year. To contextualize this estimate, we see heat within the carbon cycle. Although tropical GCP is negligible compared to anthropogenic carbon fluxes, it has a considerable weight when compared to other fluxes in riverine systems. Although the previous application may seem very distant from each other, they will represent the basis of an integrated approach for analysis of carbon fluxes of river and estuarine systems. Thank you for your attention.
Okay, thank you very much, Melissa and Luca, for your very interesting presentation. In the meanwhile, I received a question for Juan, if you are still there.
Yes, I am.
Hello, Juan. Sorry, but there is a little bit of lag between your presentation and the questions. So there was a question regarding the dimension of the disturbances of the cut that you are able to map in your study. More or less, what is the average size of the?
Yeah, that's a very good question. So theoretically, the pixel of the Sentinel-1 data is 10 by 10 meters. So theoretically, we can be as tiny as we want, but for enforcement purposes, we have make a cap of 1 hectare, because it's not worth to go to displace enforcement people to go to polygons smaller than that. So this is our cap. I guess we can lower that cap to 0.2 or 0.3. Our colleagues of Wageningen, we have a similar system in Africa. They're running with a 0.2 hectare cap.
Joan, sorry if I interrupt you. I think the question was more related to the average dimension of each cut, of each...
Of each, excuse me?
But it's okay. But we can go back to the discussion after the end of the other presentation, so we have a little bit more of time.
Absolutely.
Okay, so we move to the next presentation. Let me take back the program. So the floor is for Sergi. Is it correct?
Yeah, it is correct.
Okay, the floor is yours. Okay, we can see your screen.
Okay, perfect. Good morning, everybody. I'm Sergi Costafreda. I'm a postdoc at the research group of Professor Bindi here at the University of Florence. This presentation is related to a study that recently we submitted to the Precision Agriculture Journal. And this presentation is named Coupling Remote Sensing Derived Data and Grapevine Simulation Models for the Estimation of Intrafield Vine Variability. This presentation has been done by me and some of my colleagues, Camilla Di Bari, Luisa Leolini, Giacomo Trombi, Marco Moriondo, and Marco Bindi. But why we are focusing on viticulture? Viticulture plays an economically important role within the European agricultural sector. As you can see in the map, in the first figure, the vineyards dedicated to wine production are highly distributed in all Europe, from more or less Portugal, Spain, Sicily or Crete in the south, to Germany or Romania or Czech Republic. However, Italy, France, and Spain contribute more than 50% of the world wine production. This production varies depending on different characteristics. For example, the wine, the grape variety, for example, also the latitude. But then also this production changes year by year depending on the weather conditions. So, for example, temperature and precipitation. These changes of temperature and precipitation shows also changes in sugar and acidity content, as concluded by Leolini et al. 2 years ago. Then also implies changes on phenology. For example, in this graph of Koch et al. In 2018, we see that during these last years, these last decades, the harvest date has been occurred before the year by year, but it also occurs in other phenological stages, because all these phenological stages are linked one by the other. Then these changes are expected to increase in future. For example, Moriondo et al. In 2013 simulated that the current areas or the current suitable areas of wine production will be shifted on the future, on the north areas of Europe, sorry, like in Galicia or the northeast part of Spain, to also the northern or central part of Germany, France, and so on. And also there are some studies that concluded that the parasites and diseases will be different in future. It's not clear which will be this pattern because the temperature and the precipitation, the changes affect not only the plant, affect also the parasites and the insects. Then why can we say about all these changes? Because you usually use models like these, the ones done by Bindi et al. In 1997, or the last that is a modification of the first one done by Leolini et al. 3 years ago. These models consider the characteristics of the soil, the weather, the historical weather, but also can take the forecast weather during the next days, a midterm or the future term, and some other parameters like the biomass index, the distribution of the biomass, or how many stems will be produced by the variety, so on. These parameters changes by variety. But what happens? Usually, these models simulate one point by each field or region, because usually these taking all the data is time consuming, and in some cases the costs are quite expensive. So, but we can see that inside of the field there is some interfield variability. For example, in this photo, we can see at left a high vigor area, and at right a low vigor area. And this is also translated to different leaf areas or different productions at the end of the season, but also different accumulation of the biomass. Also is translated to the time that is dedicated to the pruning at the end of the season. This variability can be seen by using remote sensing data. In this case, as you can see in the bottom part of left, the image of a Sentinel-2 NDVI data, because usually this kind of studies use vegetation indices like the NDVI, the GEMI, or the EVI. And then we can see, or there are some studies that related this vegetation index with some characteristics of the plants. For example, in this case, in the bottom part at right, we have the study done by Colombo et al. In 2003, in which they simulated or they analyzed for some species or some land uses the characteristics or the relation between the NDVI and the leaf area index in this case. But the leaf area index can be substituted by other characteristics of the plant, like the radiation absorbed by the plant. In this case, they saw good relations with an R-square approximately of 0.75. So this is the basis of this study. And how this study has been done. First of all, we considered the model done by Leolini et al. In 2018 that is in Bioma. Bioma is a platform with a family of models in which some models can be interconnected. For example, in the model of Leolini, that is the Unificar IPML, takes the soil water content or the soil water moisture and the evapotranspiration of a package named SoilVu. Then this model is written in C#. So the model, as a result, gives some information, like for each year says that the start by break day, also the flowering date, the fruit set, the variation date, or the maturity date. Then with this information, this also calculates the leaf area index. But what happens if we want to substitute this leaf area index or the total radiation absorbed by the plant with the information related or derived from remote sensing? In this case, this is only a prototype version because we are working on this. We considered the Google Earth Engine data we consider the Sentinel-2 surface reflectant from the Google Earth Engine in the fruit set date. Then we calibrated this data with the cheptometer radiation in 3 different periods of the year. And we used this derived data from remote sensing to force the model and have the variability within the field. In this case, we selected a field that is located in Fonterutoli, near Siena, this always in Toscana, and we selected different areas that they have 2 different vigors, the upper zone with high vigor, the lower zone with low vigor. We measured more or less 300 plants in 2018. The field has the Sangiovese grapevine variety, and the density is more or less 2.2 per 0.8 square meters. Okay, we did 3 field campaigns in June, August, and September, and as I said to you before. For collecting the data, we collected intercepted radiation per each row in each of these 300 plants, then derived from the Sentinel images. Also, we used the drone images in the fruit set stage. This drone image could permit us to delimitate the canopy dimensions. And then at the end of the season, we also took for each of these plants the fresh and dry grape yield. With the drone and the Sentinel images, we covered the rows, the plants, and also the interrow. We removed the interrow with a procedure that has been done in 2012 by Maselli et al. And then we forced our model with this data. The result, we had good relations between the intercepted radiation observed with the simulated that is derived from remote sensing. We forced our model, and as you can see here, we have the variability at right, on the top at right, of the output of the FAPAR. And then, as an example, you can see on the bottom at right, the simulation of the different yields, in this case dry matter, because usually models analyze dry matter, so simulate dry matter. Okay, it separates quite good the different areas, and we have errors around 0.5, more or less. Then, with the use of this remote sensing data,
Sergi, I'm sorry. Sorry to interrupt you. We are running a little bit out of time, so if you can try to speed up a little bit. Thank you.
This is my last slide. Okay, this is a prototype. This procedure it can be done with other models, like, I don't know, for example, for olives or for potatoes. And then this can be a decision support tool for the farmer, and can tell to the farmer how is or when is the best period for determine or some specific elaborations to the soil or the plants or something like this. Okay, and I finished my presentation. This is a vineyard in southern Sweden. Is something that could be some years before it was some hypothetical thing. It wasn't present, but now it's a reality. So sorry for my delay, and thanks for your attention.
Thank you very much, Sergi. I also received a question for your presentation, but I would like to move a little bit to the next presentation, then I will come back to the questions if we have time. So the next presentation is on Earth Map. So the floor is for Laura Guarnieri. The floor is yours. We cannot hear you. You have the microphone muted. Not yet. You have to push, voila.
Okay, sorry. Can you hear me?
Yes, we can.
Okay. So, great. Thank you to the University of Florence and the GeoLab for the organization of this webinar. Thanks also to all the speakers for the excellent and inspiring presentations. Today, I'm presenting on behalf of the Land Use Monitoring and Innovation team of FAO, which includes all the people listed here. My name is Laura Guarnieri, and I graduated from this university, so I'm doubly happy today to introduce you our new web-based tool called HeartMap, developed with the support of Google and findings from the Germany's International Climate Initiative. We will see in a minute. So HeartMap is basically a Google Earth Engine interface to facilitate land monitoring, bring the big data dimension to anyone on any internet device. So we just saw through the presentation the amazing revolution brought by G, combining the free access to an unparalleled amount of Earth observation data with the cloud computing. So this is incredibly powerful, but the bottleneck is to provide the opportunity to anyone, so scientists, but also non-scientists, also without a background in programming languages, to perform those climate, environmental, multi-temporal analysis. So, which is why HeartMap was created. You will see the simple and user-friendly web interface where no programming is needed, and I would say also no remote sensing skills. So we prepare a few slides just to introduce how, after another FAO Google tool collector, how we came up with the HeartMap. But I would, since I have only a few minutes left, I would prefer jump directly to the platform. Maybe those who are interested the organizer can share the presentation later. So the first time you type heartmap.org in your web browser, you have to sign in with the Google account to have full access to all the features and functionalities of the tool. So here you can see there is this interface like Google Map, or you can choose the more Google Earth background. And so the first step is to select an area of interest here. So I can start type Italy, for instance. You have all the countries, and then the map will zoom. It will zoom into the area. You have other administrative boundaries for all the countries included. The user can also create a new boundary by manually digitalizing a polygon on the screen, or even upload a vector file in the format of zipped ship file or GeoJSON or KML. Then, once you are done with the area of interest, you can access and activate the layer that you want to display here. So the visual content of our map is organized into thematic groups. Unfortunately, we don't have time to present all the layers, but I invite you to click simply on the info button to get this short description of the data set, and then you can click on the link to get the data provider and more info. So all these are available, freely available data sets in Google Earth Engine, or okay, but I would go to the most powerful part of our map, which is on the right side. So let me, for instance, click inside the province of Florence, and you can see this right panel will open up, and just check that you select the good polygon. And so basically, this is the possibility to process data on demand, okay, in a matter of a few seconds, just depending on your internet connection, of course. So here you have to select a matrix, which is basically a script in the code editor. Just as example, let's see the maximum temperature from the Area 5 monthly aggregates. It's a Copernicus product. And then, so based on the nature of the phenomenon you want to study, you can select a temporal aggregation and also change the time range. But let's keep the default one, which covers the whole time series. So we have more than 40 years of observation for climatic variables. So just click on process. This was run on the Google Clouds. And also the time you can launch the time series and the monthly average, just to show you the three way of generate statistics. So here we can immediately notice an upward trend in the maximum temperature, and you can also download, maximize the chart, and download, export data as a CSV for further analysis. And okay, you can also, let me maximize this monthly time series. So you can zoom also, you can zoom on the in a desired reference period. You can focus also on the deviations, and we can immediately notice, let's say, prevalence of a positive deviation, meaning an upward trend for maximum monthly temperature, etc. Let me just show you another thing of our tool. So we have the possibility to open the area of interest also with this handy-name FIO geospatial platform, which contains a huge database, FIO database. And we also build this imagery comparison tool, which is basically Google Earth Engine application. Let me show you here. So this is, you have rapid access to multiple Earth observation services. You have some showcases here. Let's check the recent Etna eruption, just as an example. So when you choose an example here, of an event, this is useful to assess the impact of, as you can see, extreme events or climatic disaster. So for this one, the Etna one, so for the example, the sensor is already set for you to optimize, let's say, the visualization, but the user can choose another sensor or another band combination, so depending, of course, of the phenomenon that you want to monitor. And so there was a last eruption last week. So let's see, it was on 1st of April. So we can just jump to a date. Let me select the 1st of April. So here you have also the plus info button to explore info about each sensor. So this is the spectrometer Sentinel-5, which measure all, in this case, the sulfur dioxide concentration in the atmosphere. And okay, let's close it. So here we are with the last eruption, and then you can also, through this image, you can also monitor the displacement of the air mass. And we have also, for instance, floodings example, and you can move anywhere in the world. So with this freely available app. So this is the white area, is the flooded area. You can also measure something, and then, for instance, you can open or download your area of interest with KML. We will open in Google Earth for historical images. So in conclusion of this demo, let me just share with you two examples of application of EarthMap. So here we are in the southern eastern Morocco, in the oasis of Esna. I just drew a polygon. And so this is the Sentinel-2 false color 10-meter resolution image, mosaics image, which highlight the vegetation. As you can see, it's a cropped area. And if we play a little bit with the opacity and activate this radar image below, we can see the traces of Kanat, of Khetara in Moroccan. These are ancient underground water channels. And today, these systems, unfortunately, are all not working. So drip irrigation has been introduced. So you can see here on the ground the traces of those Khetara, and drip irrigation has been introduced. So this lead to an increase in the crop yields. So we have also the net primary production data set from FAO Vapor. So I already prepared some graphics for you. So we see the biomass is increasing, but farmers are pumping underground water almost without no running costs, thanks to solar energy and no government control. So this leads to an over-exploitation of aquifer. Okay, so we can see the gross biomass water productivity is decreasing, meaning that we are consuming too much water. So drip irrigation doesn't mean alone sustainability, no, in this case. And FAO data sets from Vapor are included in the water session of EarthMap. So here we can see the values of the water productivity decreasing. Another application, I don't know if I have time, but it was the object of a publication of the Lake Chad. So I think I'm running out of time, sorry. So just to tell you that thanks to EarthMap, we discovered that the Lake Chad is stopped shrinking, and it is actually stabilized, and also vegetation is auto-recovery. So we propose to include this area in the gray-green wall interventions, and so we can measure, assess the restoration potential also thanks to this amazing data set published here in the Global Tree Restoration Potential. And I think I will stop here. So I hope I could provide an overview of main functionalities of EarthMap. There are new features coming very soon concerning the uploading, downloading, and sharing of data. Just to tell you that the development of EarthMap is demand-driven. So if you have any suggestions and any requests or needs, you can just click on the Help Center, click on Contact Us form, and send us your comments or questions, which are always welcome. I think I will stop here. Thank you very much for your attention. If there are any questions, I will be happy to answer later.
Okay, thank you, Laura. Thank you very much for this very interesting presentation / demonstration of your application. Very interesting. But we have to move forward to the last presentation of this session. So I would like to give the floor to James Daniel. If James Daniel is...
Thank you, Gerardo. I'm just...
Hi, James.
I'm trying to share my screen right now.
Yeah.
Right. Well, looks like I have some trouble sharing the screen, so you can share. Just a minute. I'll do a few system preference checks here. Yeah, I was just walking a few minutes ago. Technically, I would want to introduce myself as I solve this. My name is James Daniel. I am the founder and CEO at Region International. We are a social impact company that is leveraging a lot on artificial intelligence. And can you hear me well?
Yes, we can hear you, but we cannot see your screen.
Yeah, I'm working on it. So what we do basically is supporting a lot of private sector and NGOs with technical support on climate accounting, specifically biomass carbon accounting. And we use a lot, I think there is a technical problem. I apologize for this. It was just working a few minutes ago. So what we've done is we've developed a technology that leverages on Earth engine data sets, particularly Sentinel and Landsat, to help in quantifying biomass carbon stacks on landscapes. So this is a technology that has been built basically from the previous FAO approach, Collect Earth. We saw what Collect Earth was doing, but we had a few complexities on how to put the groups together, most especially when you want to do remote assessment of different locations. So together with the Gates Foundation, in 2018, we partnered and put together imagery processing tool that is able to put together tree cover density data sets remotely. It runs on a CNN model where you can basically bring very high resolution images of between 0.2 meters to 0.3 meters, gather a lot of data on tree cover and land cover, as well as crown measurements. And use
James, sorry if I interrupt you, but do you want that we can move your contribution, your presentation to the afternoon so that you can try to
yes,
solve
I suppose
your
so.
problem?
Let me try to work on this because it would be great for you to see the presentation.
Yeah,
so,
or you can send
wait.
me your presentation, and if there is no other.
Right.
Okay.
Yes.
Okay,
yes,
so
I
at
would
2:30.
I apologize for this. I see at 2:30.
Okay, James. So let's move your presentation to the beginning of the afternoon session at 2:30, if you agree.
Sounds great.
Okay, thank you, James. Okay, so thank you everybody for your presentation. It was very interesting morning. I think we have a couple of questions that are solved now in the comments in the chat. So there was a question regarding the average size of the clear cut in Brazil, and Joan already answered 3 hectares with a median of 1.7 hectare. And Sergey answered no, for the moment in this first version we have focused on the aerial part of the vegetation, because there was a question coming from Lorenzo Marziani from University of Siena regarding the relationship between remote sensing data and below ground characteristics such as the root density. So I think that we solved also this part of the questions. So it was a pleasure. Thank you everybody, and we start back the second part of this workshop at 2:30. So we will have one presentation and then the didactical part, let's say the short introductory course introducing Google Earth Engine. So have a good lunch, and see you later at 2:30. Goodbye everybody. Thank you. Okay, good afternoon everybody. Here we are back again to this workshop on Google Earth Engine. So now, as you may remember, we give the floor to the last presentation of the morning session. So the floor is for James Daniel. Please, Daniel.
Thank you, Gerardo. I apologize for the technical glitches before. We had a big storm here in Nairobi last night, and all transformers are blown out, so it's tough to get good internet connection. But regardless, I'm ready to proceed. Like I was introducing, Rigid International, we leverage on engineering experience and support, and part of support technical works to build the capability of private sector and INGOs in climate accounting, as well as in biomass energy engineering, where we all leverage from the use of Earth Engine in different ways. So the genesis of our carbon accounting technology starts from our work with the Gates Foundation since 2018. We were invited at the Intellectual Ventures Lab to come into an advisory platform where we were developing means to monitor agroforestry practices, as well as natural regeneration practices on landscapes. At the time, we were mainly using FAO Collect Earth approach, to put together training data and bring it on the Earth Engine platform and do supervised classification and accuracy assessments and checks. And so we've made some advancements in terms of the technology that has come out of this, which is we can be able to track biomass carbon at slightly higher resolution than what Google Earth imagery provides, which is between 20 centimeter to 30 centimeter. And as well, we have relatively higher precision compared to in situ measurements of carbon. We are almost at par, but we can do this, remotely. So the technology mainly is an imagery processor that has been built on a CNN model that just, uses a patch classifier to identify this is a tree or no tree, and this is perhaps a cropland or a bushland, just by running over, very high resolution images. This thanks to the support from the engineering team at the Intellectual Ventures Lab of Gates Foundation, we were able to put together this particular technology. And right now, we've had a lot of interest, including some of the carbon standardization bodies like Gold Standard and VCS, wanting to leverage on this particular methodology, most especially during the hard times of COVID when travel has become quite limited. And so we're pretty much, leveraging on the Earth Engine platform, to showcase some of the, works that come out of this. So the CNN model basically is just putting together the data in the same way Collect Earth would have done, but then we come and do a lot of the analysis on Earth Engine platform. So one place where we've tested the technology is in Tanzania, where we worked with Plant with Purpose. Is one of the NGOs doing a lot of restoration works and farmer managed natural regeneration, as well as afforestation and reforestation, to test out how the technology, performs. We integrated both the use of very high resolution imagery, and for historical images, we just used the imagery from Google Earth Pro, and we were able to assess, the change in tree cover, land cover, as well as biomass carbon between 2005 and 2019 for this particular watershed. For Plant with Purpose, it's at the foot of Mount Kilimanjaro in Tanzania. So what we found out was how the technology was performing vis-a-vis the visually annotated data, and we found it was quite consistent. Now this technology is very, very highly customizable, because what happens is once you've put together the data sets, which is mainly tree cover, land cover, and perhaps ground measurements from aerial imagery, then we add in allometric questions that are tailored to individual agroecological zones. And then we use that to establish biomass carbon on landscapes. So the CNN model can also be able to identify between shrubs and trees. So it's a work in progress, but so far in the few tests we've done, because we did also a previous study in Ethiopia, we saw this was working very well, and we are very much excited to explore with different groups such as the USGCD who are coordinating the Great Green Wall Initiative on how this tool can be able to cut back the budgets for performance assessments. So it's very much easy to use, and we are working towards automating it at this particular stage. It's still flying pieces, but it's performing very well, and it's also having a very much complete synchronization with the Earth Engine API. So, for instance, like I mentioned, we leverage from land use change and tree cover change data sets, but we analyze on Earth Engine, and then we use those particularly to establish a lot of what the context would be like on biomass carbon accounting. So we are very much open to doing a lot of tests and trials with different groups in different parts of the world to see how the algorithm is performing. The thing that is interesting about this technology is that for every other region you are going to work from, you have the opportunity to create for yourself your own training data, and then you use to calibrate the algorithm, and then you can use it over a vast landscape. And without being there, remotely, of course. So for level 1, we put together the land cover and tree cover data sets. We try to check how the accuracy levels look like on Earth Engine platform. And level 2, we basically bring in the allometric questions that come in 2 different tiers, most especially leveraging on the iteration that increase in tree cover provides proportional increase in biomass carbon stacks. And then for the second iteration, perhaps we bring in the iteration that we can leverage from ground measurements that come from aerial imagery, to provide the biomass carbon quantification. So this technology at this particular stage is only usable in above ground biomass and below ground biomass, context. And it's also very much guided by the IPCC good practice guidance. One thing to realize is we've almost, ruled out the opportunity that you'll start to work from tier one, because you can literally create for yourself your own data, provided you can access the very high resolution images, and then start working from tier 2 all the way to tier 3. So when you have species data and maybe crown measurements and other additional data types, then you are bound to select allometric questions that can get you to go that particular level of detail. So it's very, very flexible, and you can keep to improve the accuracy as you go forward. Some of the results that came out of the analysis that we did for Tanzania are presented up in the year 2005 and in the year 2019. In general, we found there was an average increase of biomass carbon by about 13.87 tons of carbon per hectare between 2005 and 2019 in this particular watershed. Like I've mentioned, the technology is mainly leveraging on the stock difference methods, and also having to treat different land cover strata with various allometries. But generally, for tier 2, where we start working from, we say we use the linear algorithm for tree cover to biomass carbon conversion. And then for tier 3, we use the carefully selected aerometric equations for crown measurements that are built on logarithmic functions that also factor in coefficients that vary from very agroecological zone to another. We have done a few checks to see our accuracy assessment on Earth Engine. So Earth Engine has become very handy for us in this particular way. I would have wanted to talk so much in detail about the technology, but I made it very brief based on the 10 minutes available. So I would just want to talk a bit about the schema of the technology. So we basically get our imagery put together using the imagery processor, and then we do our initial statistical analysis. We try to validate if the data is looking very well in proportion, just from, if we can access localized knowledge, or if we can be able to drill down to these locations with other global data sets available on Earth Engine as well, that might not be at very high resolution. Once we're comfortable, we can keep the data in a specialized database. The next stage is we transfer all this to Earth Engine into our supervised classification, as well as accuracy assessments. Once we're very much comfortable and these are in line with our statistics, then we can put this on our restoration platform, where we have most of the data that we use to develop reports. With these particular maps, we take them to another additional stage of validation. When we have corrective actions, again, we cross-check and come up with our carbon stacks numbers, which we also present on we stay in our restoration platform as well. Further to all this, the most important is we develop competent reporting standards, which we also pass through expert review if needed. If maybe we suspect there is a lot of maybe anomalies that are getting out of the data, and then we do our finalization and display the data on our dashboard, which is mainly also using Earth Engine API. So Earth Engine has become very much important for us because I think this particular technology is becoming very popular for providing solutions to NGOs and private sector. I believe that is my presentation.
Okay, Daniel, thank you very much for your contribution, and thank you very much also for a very early wake up this morning, I guess. So,
right.
Thank you very much. Okay, now it's time to move to the second part of this workshop, that is for the course on the introductory course on the use of Google Earth Engine. So I invite Saverio.
Hi all. As I said this morning, I am Saverio Francini, a PhD student from the University of Viterbo and the University of Molise, but I'm working at the University of Florence. So this will be a workshop for beginners, so we'll show very simple things, but we'll try to show you also some advanced tips.
Sorry, I just have to mute.
Yeah. Okay. So, as I said, we'll see a number of things in this hour together. These are the main topics that we will see together. We'll start to see how the Google Earth Engine code editor works. Then we'll start to see some basics of JavaScript. We'll write a code together to see how this works. And then we'll start to visualize Google Earth Engine data. After that, we'll finally see how to filter datasets. In particular, we'll use the Sentinel-2 dataset. That is, filtering dataset is one of the most important things in Google Earth Engine because, as you know, there is a huge amount of data available and filtering this data is mandatory. After that, we'll try to construct cloud-free composites that...
You're muted.
What? Yeah, but I think that... see? Oh. Okay. Okay. Yeah. Sorry, one moment. Non usavo perché usavo questo.
No, questo va sulla... Sì, questo va sulla cosa. Sì, ok.
Yeah. Okay, so sorry. We were on the cloud-free composites calculation. The cloud-free composites calculation is a first very important step when you want to apply remote sensing algorithms over very large areas. And sorry, one moment again. Everything is fine? Yeah? Okay.
Sì, dal Meet non deve più uscire. Sì, va bene così.
Okay. Okay. So, sorry, cloud-free composites calculation is a very important first step if you want to apply algorithms over very large areas, and if you want to move analysis from sham-based analysis to, for example, continental analysis. After that, we'll construct together a function that allows to use the cloud-free composites calculation code with different input parameters, so that we'll write a function together that allows to define different composites using, for example, selecting images acquired in different periods or using a different cloud threshold. Finally, we'll try together to develop a user-friendly interface.
Renato, you're still muted.
Sorry? Costanza, mi si sente su... Ok. Yeah, so a user-friendly interface, so a panel that allows to define the inputs that our cloud-free composites calculation function require. We'll try to see these codes together. Anyway, we'll see a lot of codes, and I'm not sure if you'll be able to follow me for this reason, but don't worry, because all codes are available. All material of this workshop will be available for you. To find this material, you have to go to the Copernicus website. You have to open the event of today. Then you'll find all the material will be uploaded here. And then here you'll find the presentations and also the links of this workshop, also the links that we are going to see together. So as Noel Gorelick said this morning, one of the advantages of Google Earth Engine is that it allows to show results with other researchers. One of the way to do it is to construct applications. So we'll try to construct this very simple application together. That is an application that serves to construct cloud-free composites using Sentinel-2 images. And this is a screenshot of the application. So we'll define this application that allows to define different years and to define different periods to acquire images, and also different cloud threshold to select images. This application allows also to visualize different 3 bands combination. In this case, we are looking at a false color composite, and for this reason, we selected red, green, and blue. But in this other screenshot, for example, we are selecting 3 other bands. So I'll try to use directly the code editor to show you all the codes and all the calculation. However, the waiting time required to see the results depends on the amount of users that are using Google Earth Engine in this moment, and also on the amount of servers that are available. So I hope that we'll not have to wait too much time to see the outputs, but if it will happen, I'll show you the output of the codes using this presentation. So I have already saved here the outputs. So as we suggested you should have created an account, a Google Earth Engine account. This is the code editor. On the left, you can see there are 3 main windows. The left window is divided into scripts, documentation, and assets. You can create new scripts clicking on the new button, and scripts are the file that you can use to define your JavaScript codes. The documentation is what you can use to see all functions that are available on Google Earth Engine. And the assets is indeed where your own data sets are stored. You can upload images, shapefiles, or CSV files. You'll see this better later with Giulio Castelli. Here we have where you will write your code and where you can decide to run the code, to save your code, and or to share the link of your code. So getting this link and sharing this link with other researchers will be able to execute your code, to edit your code, to copy your code, and to run your code. On the right, there is another panel. So there is the console, that is where outputs are displayed, and outputs of your code are displayed, and there is the inspector. So the inspector allows to see the values of the map. In this moment, we are not visualizing any calculated map. Anyway, if you click on a point, you are able to see the longitude, the latitude, the zoom level, and the size of that pixel at this zoom level. If, for example, I increase the scale, I'll see that the scale is changed, and also the size of this pixel at this size. As Noel Gorlick said this morning in Google Earth Engine, the calculations, the scale at which calculations are performed depends on the scales at which outputs are requested. So if you want to visualize outputs at this zoom level, the scale to perform the calculation will be much larger. Okay, we'll start to write some JavaScript code together. As a first thing, we'll see how to write a comment. So if you want to write a comment, you'll have to use the double slashes. If you want to write a multi-line comment, you'll have to use asterisk and slash. Okay. Having said that, to create variables in Google Earth Engine, you'll have to write var, meaning that I want to create a new variable. After that, you'll have to specify the name of your variable. Let's say name of variable. And then you'll have to use the symbol equal to say which value you want to use for this variable. Let's say a number. If you want to print your variable on the console, you can use the print function. Yeah. After each line, you should use the semicolon, and Google Earth Engine suggests you to do it. If we click run, we'll see the output in the console. An important thing of Google Earth Engine is that you cannot choose which line you want to execute, and when you click run, the whole script is executed. In Google Earth Engine, you can define lists. So, for example, L and list are defined using square brackets. You can print, of course, also lists. For example, it is quite simple also creating images. For example, I want to create an image which name is img, and to create an image I'll have to use the ee.image function. The ee.image function is a Google Earth Engine function, a built-in function, and to see what this function does, we can use the documentation. So this is a function that can take different arguments, can take as arguments an image, a list of objects, or a number. We used a number, and we can print this image in the console as before. We have one image with one band, and this image has just one value, that is 3, and that is an integer. We can also visualize this image, and to visualize this image, we'll have to use the map.addLayer function. The map.addLayer function is another built-in function of Google Earth Engine. We'll see this function better later. So if we calculate this map, we can use again the inspector, and we'll see a value of that is 3 everywhere. Okay, I think that the boring part is over. We can start to see how to visualize images. We can save the script. So as I said, you have the link for this repository. So this Google Earth Engine Networking Day repository includes 6 files, and you have all these files. Okay, we'll try to open 2 datasets, a digital elevation model and a forest, no forest, and water mask. To create a digital elevation model image, we'll have to specify var, then the name of the variable we want to create, and then, as we saw, the ee.image function can take as argument also the path of Google Earth Engine datasets. When you are uploading a Google Earth Engine dataset, when you are loading using your script Google Earth Engine datasets, you are able to convert these datasets as an import record. If you do it, you will see your datasets appearing here. This is very useful because in this way you can click here and you can see the description of your datasets, what bands are included in these datasets, and a lot of useful stuff. Here we use the ee.image collection because these datasets, it's not an image, but it's an image collection. So it's a list of images. Indeed, if we go here, we'll see that the dataset availability of this forest no forest mask is between 2007 and 2018. If you go to see the bands, we'll see that these images have just 3 values, pointing forest, non-forest, and water. We want to visualize just the first image. We don't want to see the whole image collection. And this is very simple. In Google Earth Engine, we just have to use the .first function. Again, if we want to see what the .first function does, we can use the documentation, and we can see finding an image collection because we are applying the .first function to the forest variable that is an image collection. We can see that returns the first entry from a given collection. That's it. After having selected this forest mask, we want also to try to perform a Google Earth Engine calculation instead of just visualizing a dataset already available on Google Earth Engine. To do it, we want to calculate the slope. So we will use the ee.terrain.slope function to calculate the slope from a digital elevation model. To see what this function does, again, we can use the documentation. And this function calculates the slopes in degrees from a terrain digital elevation model. Okay, that's it. We have created 3 objects, a digital elevation model, a slope, and a forest, no forest mask of 2007. Now we want to visualize these 3 layers. To do it, we'll use again the map.addLayer function. As I said before, the map.addLayer function takes a lot of arguments, but the most important arguments are 3. The image that you want to display, the input parameters to use for visualization, and then the name of the layer. In this case, we are not visualizing just the DEM, but we want also to mask out pixels where the digital elevation model is equal to 0. Or in other words, we want to visualize just the pixels where the DEM is greater than 0. The same thing for the slope. After that, so we can click run in the meanwhile, we want to visualize this image using these input parameters. So this is the digital elevation model. Then we are saying here that we want that pixels where the digital elevation model is 0 are brown, then pixels where the digital elevation model is 2000 are white, and then pixels where the digital elevation model have values of 1000 are yellow. Same thing for other datasets. So here we want to visualize the slope, we want to mask out pixels where the slopes is 0, such as, for example, in the water, in the oceans. And then we want to use these input parameters. So we want to use to visualize pixels with a slope of 0 in brown, pixels with a slope of 30 as white, and so on. After that, we want to visualize also the forest, no forest, and water mask that has 3 values. It is a categorical map. So defining 3 colors will be able to visualize a categorical map showing a different value for each color. This is the digital elevation model, and you can see it is visible everywhere in the world. In this case, Google Earth Engine is not performing any calculation. We are just visualizing a data set that is already available. Differently, if we want to visualize, if we go to visualize the slope, this image is calculated on the fly in this moment in the Google servers. Also, again, as Noel said this morning, the scale at which calculations are performed depends on the scale at which you are trying to visualize the outputs. And when you change scale, the calculation is performed again. Anyway, as you can see, the calculation is performed very fast. So simple calculation in Google Earth Engine are performed very fast. And same thing for the forest, no forest mask. Yeah, this is the categorical map. We are looking at the 3 colors we defined here: gray, brown, and blue. Okay, we have also saw how to visualize simple images, and we want to try to do some more interesting stuff. We start to see how to use the Sentinel-2 dataset. So doing it is not very different from what we did before. We have, first of all, to load the Sentinel-2 dataset. The Sentinel-2 dataset is an image collection, so we'll have to use again the ee.image collection. Then we'll have to use the path of the Sentinel-2 image collection. As before, these input datasets can be converted as an input record, and if you do it, you'll be able to click here to visualize the description of this dataset, the dataset availability, and also the bands that are available and the properties of the image, among which there is the cloudy pixel percentage. After that, we want to pick just images acquired between June and August. So the Sentinel-2 datasets here consist in all Sentinel-2 images acquired in the world. Here using this function, we are able to pick just images acquired between June and August. And using this other function, we are able to remove images that are masked, that are covered by clouds more than 10%. In other words, using this function, we are saying that we want to filter images looking at the cloudy pixel percentage property, and we want to pick just images that have a value of this property less than 10. If we click run, we should be able to see the output of this function. Anyway, I already have saved this here. And after filtering this Sentinel-2 image collection, there are about 400,000 images in this image collection. Indeed, here we specify our filtered image collection, and then we are using the dot size function, and then we want to print this. Indeed, in the console, we can see about 400 images. So a huge amount of images are still included in this image collection. After that, as you can already see in the map, we decided to visualize the image collection and then the median. So This image collection includes a lot of images, so there are a lot of pixels where a number of observations are available. If we display just the image collection, we are actually looking for the first available information for that pixel, where in this case the first is the last one acquired. As before, we can define visualization parameters. We define the minimum and maximum value to define colors, and then the 3 bands to use for visualization. And these bands are red, green, and blue. And then the name of the image of the layer that can be seen here. Yeah, because a number of observations can be available for the same pixel, a better solution compared to just visualizing the last available observation is to calculate the median of these values. And that's what we did here. So here we are looking at the median. And here we are looking at the initial image collection, that one. As you can see, this image is much more cloudy compared with this one. Anyway, also in this composite, in this image, there are still some clouds. There is still some noise. This is because we did not mask out clouds, and we are just calculating the median of a lot of images, some of which are cloudy. To obtain a better cloud-free composites, that is the aim of this demonstration, we need to mask out clouds. To mask out clouds, we'll use this other code, and we'll see how to do it. As before, we'll use the same exact code as before, so we are loading the Sentinel-2 image collection dataset. We are filtering images acquired in this period, and we are removing imageries that are covered by clouds more than 10%. To mask out clouds, we want to use the Sentinel-2 cloud probability dataset. So this dataset allows to use a different forest mask for each, a different cloud mask for each image available in the Sentinel-2 image collection. This is the Sentinel-2 cloud probability dataset, and you can see this dataset returns between 0 and 100 the probability that each pixel is cloudy. This dataset is created using a machine learning approach and is very precise. So I suggest you to use this dataset instead of the cloud mask available in the Sentinel-2 image collection datasets. Okay, to mask out clouds using this dataset, we have to join these 2 images collections. So we have the image collection with Sentinel-2 images, and we have the image collection with Sentinel-2 cloud masks. To join these images collection, we have to use the ee.join.savefirst function. This function takes one argument, that is the name of the band that we want to use to attach the cloud masks to the Sentinel-2 images. After that, we'll use the apply function, and we'll have to specify what we want to join. So we want the first image collection that we want to join is the Sentinel-2 image collection, and the second image collection that we want to join is the Sentinel-2 cloud probability image collection. After that, we'll have to specify a condition. So what is the condition that should be followed to define with which image each image should go? So here we are using a filter equals. So we are saying that we want for each image in this image collection to find an image in this image collection that has the same system index. Indeed, we are looking for the system index in the first image collection and for the system index also in the second image collection. The system index is the unique name that each image in the Sentinel-2 image collection has. Okay, we have obtained a Sentinel-2 Cloud Mask image collection, and we can go ahead and define a function to mask out clouds from each image. So we have an image collection where each image has a cloud mask band. As a first step, we have to define a function that needs then to be applied on each image in the Sentinel-2 with cloud mask image collection. To define this function, it's very simple. We have, as always, to say that we want to create a new variable, then the name of this new variable, that is mask clouds, then the equal symbol, and then we are saying that this is a function. Then we have to specify the argument of this function. This function takes just one argument, that is an image. Then we have to say what we want that this function does. This function in the first line has to select the clouds probability band available for the image. So we get the band image.get, and then we select just the probability band, because if we look at the Sentinel-2 cloud probability dataset, we'll see that the name of the band is probability, and that's why we are actually selecting probability. After that, we have to define a mask using the cloud probability image, and to define a mask, we'll use again the less than function. So we want to mask out pixels that have a probability to be cloudy greater or equal, actually, than 20. And because this is a function, we need to specify what this function should return, and to do it, we'll have to use the return function. So the output of this function should be the input image, and indeed you can see here the input image, but masked using the isNodeCloud mask. Okay, that's it. In Google Earth Engine, once you have defined the function that is ready to be applied on each image in an image collection, you just have to use the map function and do it. You don't have to care about the fact that this image collection can include hundreds or thousands of images. So we create a new object. The name of this new object is Sentinel-2 Summer 2018 Clouds Masked. And then we use the map function on the Sentinel-2 with cloud mask to apply on each image in this image collection our mask clouds function. Okay, that's it. Now we have click run again. We'll have to wait a little bit of time probably, because as I said, the waiting time depends on the amount of data and on a lot of things. Anyway, here we are using again the map.addLayer function to visualize three different things. The first thing that we are visualizing is the Sentinel-2 Summer collection dataset. That is the same dataset as before, so the whole image collection. And looking at this one, we are visualizing the last available observation, the last Sentinel-2 available observation. Here we are calculating the median as before, but this time this median is calculated over an image collection from which clouds were masked out. So this image should be much more precise. And then we are visualizing the same image. As you can see, the image is exactly the same. So it's the median of the clouds masked of the observations available in this image collection. But we are using different input parameters. So here we are visualizing a false color image, while here we are visualizing a different three bands combination, and the name of this composite is agriculture composite. This is the agriculture composite, as you can see, and this is the RGB composite. So you can see that the amount of clouds is less compared to the images before. That's because this time we masked out clouds. And yeah, here this image that that is calculated in this moment in Google Earth Engine is the initial image collection from which we did not mask out clouds. So what we can see here is the last image acquired by the Sentinel-2, and for example here it was cloudy, while here clouds were masked out, and then the median of all available observation was calculated. So this is a cloud-free composite that can be used for further analysis. And however, it is important to say that we are using a median. That is a very simple method to calculate cloud-free composite, but actually it's not the best one. There are other available methods. For example, the best available pixel method that allows to define which pixel should be used on the basis of different criteria. For example, the distance from clouds, the date of acquisition. Anyway, this composite is much more simple, and it was more suitable for this demonstration. Okay, we have created this code that allows to construct a cloud-free composite, but this code can still be improved, in particular because using this code you are able just to create cloud-free composites using images acquired in this period, using this cloud threshold, and masking out pixels where the probability to be cloudy is greater than 20, and at least you can visualize just these 3 bands combinations for composites. We want to be able to use this function with different input parameters, and so we have to construct a function. To construct a function, we have already seen how to construct a function. So, how to construct a function? To do it, we have to use var. So, again, saying that we want to create a new variable. Then we have to specify the name of this new variable, that is calculate composite. And then we have to use the equal symbol. After that, we are saying that we want to create a function. And as before, the arguments of the function. Before the argument was just image, because we wanted to apply that function on a lot of images. But this time, this function takes a lot of arguments. You should be able to see that these arguments are exactly the arguments that our cloud-free composites calculation code needs. Indeed, we can define the year to construct the composite, the period, so the start date and the end date, then the cloud threshold. Indeed, before here we were masking out images covered. Here we had 10 before, but now we have this parameter so that a user can specify a different cloud threshold without the need to write again the whole code. Same thing for the mouse clouds probability. Before here we had 20, and now we have this input parameter. At least, but very important, we can visualize different bands using these arguments, and we can use different minimum and maximum values in this line. Having said that, this function is exactly the same as before. So it's exactly the same code we saw in the script before, but just ported into functions. So actually, we added this line, then we defined these arguments, and we replaced the numbers that for example, here we had 20. We replaced these numbers with the arguments of the function. Because we want to use this function from other scripts, and we want to be able to use this function using these different parameters without the need to write every time again this code, we can use the exports function. The exports function is a very useful Google Earth engine that allows to keep your codes clean, so that again you don't have to write again the whole codes. In this way, you are saying that you want to export this function, and the name that you want to use for this function is the same. I decided to use the same name. I usually use the same name. Okay, in this way we can use this function from other scripts, and we'll do it. Okay, we have created a function that allows to construct different cloud-free composites, selecting different periods, selecting images acquired in different periods, using different clouds threshold. But because we want that users can use this code, this function, also without the need to use the code or to know the JavaScript programming language, we want to construct also a user-friendly interface or an application. To do it, the first thing that we need to do is to construct a panel like this one. Constructing a panel means that a user is able to define input parameters using this window without the need to see the code or without the need to use the code. For example, here you can define the year, you can define the period, for example, that period, you can define the bands that you want to visualize, for example, these three random bands. You can define the clouds threshold, the clouds probability, and the minimum and maximum value for visualization. And then you have just to click run. So to construct the panel, yeah, this can require some time because we are using all Sentinel-2 images acquired in the world. To construct that panel, it's actually quite simple, and we'll see this part very fast. Anyway, you have the whole code, so you'll have time to carefully check that code, and I hope that you'll be able to use these codes to construct your own application to show your own results. Yeah, so we have to construct a panel. To construct a panel, we have to define the title, and to define the title, you have to use this function. Then you have to define a selector, and to define a selector, you'll just have to use this function, and so on. After that, as you define this selector, you are able to define these selectors. So it's quite simple. Then we need some text boxes like this one, and it can be done using this code. You just have to replace some arguments, and then you can construct different text boxes for a number of different applications. We can use also sliders like this one. This is a slider, and you just have to use this code, define the minimum, maximum value, the step, and so on. Okay, once you have defined all objects that you want to put in your panel, you have to construct the panel, and to construct the panel, you have to use this function, and then you have finally to add all objects to this panel. To add objects to this panel is, again, very simple. You just have to use the add function. And at the end, you have to display the panel with all objects in the map. And to do it, you have to use this function. Okay, we are near to the end. Because we included a run button that is here. This run button should be here. This run button, for this run button, we use the onClick function. So when you click on this run button, that is this one, the run function is executed. This is the run function. When the run function is executed, actually the load inputs function is executed. And the load inputs function simply get the values of the objects you defined in the panel. So it creates the objects that our cloud-free composites calculation function requires. So once the load inputs function is executed, and it happens in the run function. Inputs are in a dictionary. That is a Google Earth Engine object, actually a list. Here we print the list, and indeed here you can see that its job object includes the parameters we defined using the user interface. As we said, we wanted to use the function that was available in the other script, so to do it we have to use the require function. And the require function takes as argument the path of the function, and that is the path. Yeah, we are ready to apply our function because we have all parameters within the inputs object, and we have the function. So that's it. That's what it happens when you click on the run button. This is a very simple application, but I hope that you'll be able to editing the codes that we give to you to construct your own applications. Yeah, this is not exactly an application. This is a user interface. If you want to obtain an application, you can use this button. It's very simple. You just have to click new app, and then you can define the name of your application, the image, the description. Yeah, the main differences between applications and this kind of user interface is that applications can be used also by users that don't have a Google Earth Engine account. On the other hand, using user interface like this one, you are able to edit your code, to edit the user interface, and then the application. If you want to share this kind of code, you can use the get link, or as I did for giving you the material, you can share the whole repository clicking here. And for example, defining anyone can read and sharing this link. Okay, that's it. I hope you enjoy it. It was a very quick presentation, but just for beginners, but I hope that it will be useful for you, at least for start using Google Earth Engine, and then learn much more about it. Thank you very much.
In this part, we will develop another functionality of Google Earth Engine. And this functionality is about the use and the downloading of time series. So the basic advantage of Google Earth Engine is that being a cloud-based computing system, it offers the possibility of interacting with the large data sets. And what is useful for many users is just to have the results of these data sets visualized and downloaded on their laptop as time series. That means calculating or maybe analyzing the evaluation of a type of variable in a given point at a given time for a number of replications. So as we have already said, Google Earth Engine is a platform for Earth system science study. We already have a large number of data on Google servers, and we made a lot of calculation on Google servers. We have also the possibility of loading shapefiles, so namely areas, vectorial GIS data, from our local system, and this functionality is particularly useful for our applications. So I have a couple of links. Costanza, do we have the possibility of share the links despite the problem with some chat? Okay.
So, but just now? Okay, so and the users, the registered users can access? Okay, so I'm just going on the drive. I think the drive is in your email. So I'm just sending you the data that you need for this lesson just on the shared folder. So in this moment you have the presentation that I'm showing just directly on the shared folder of the workshop, and you can use the links to download and access the data that we will use. So let's go back to our presentation, and let's finally start with Google Earth Engine. So you can see here the platform that we have already seen before with Saverio together. And we are just now basically analyzing which are the potentiality of this tool for time series analysis. So let's start and let's do the first thing. So first of all, you have to access the Google Earth Engine code editor, and we will start by creating a repository. So we access Google Earth Engine, you click on New, and we create a repository. So this is just a basics of Google Earth Engine data management, but it's quite a useful thing. And we create a repository, which is basically a folder, and we give a name lesson. So it may be that Google Earth Engine asks you to specify your username before, especially if it's the first time that you are accessing the system. But what you will have after this operation is basically your first working folder on the scripts tab. So let's see how we create one file. We just go to New again, we go on File. You see that the default path to the file is the one that we made together, so our folder lesson. And we just recall the first file, exercise 1. So basically, another quite useful thing of Google Earth Engine is the map. The map is very interactive, it's basically based on Google Earth database. So it's basically Google Earth embodied in your code editor. You can move the map, you can select a satellite background or the basic map background, and you have also some drawing instruments, and we will see that this latter one will be quite useful just in case we have to analyze time series. So let's try to add one point on the map. That can be done with this tool, add a marker. And what you can do basically is to put one point anywhere you want. You see that immediately the Earth Engine code editor converts your action into a code. So if you draw a point here, you will see that in the script that you have created, let's go, to exercise 1. So let's do this thing with exercise 1 script. You have to click here. So if we do this thing within our script, Google Earth Engine creates for you a line of code that says that you created a geometry. The geometry is a point, and the point has some coordinates. You can also rename dynamically your objects. So if you click on the name and you change the name, we will give here the name target, you can easily change the name to your variables. So you can see here that we have renamed your geometry to target, then you can save the scripts. So just an important thing, Google Earth Engine files are called scripts, but they are dynamic text files. So whatever action you take within the code editor, what happens is that you manage, and you will see that your basically your script change by your action on the code editor. So from now on, we will refer to this part that we are writing, the exercise 1, as script. So what we can do is also to search for dataset. And what I want to do is to create a time series of normalized different vegetation index. That is called also NDVI. You see here that it's very comfortable. You can look for files, you can look for collection of data, and you can even interrogate this collection of data. So what I want to use is basically one of the last products that you find here, that is basically Landsat 8 32 days NDVI composite. If I click here, I see my data. I can also click and go to a documentation page that explains me all the algorithm behind this data, and I can import. If I click import, my script is updated dynamically. So you see here we selected this 32-day normalized different vegetation index composite. And what we do, we just rename this second file that we have in our script with a new name that is L8 NDVI composite, just to know what we are working with. And you see that we basically have two variables in our script. So what you can do is also to expand your variable and to check all the data. So you see here that is an image collection, so a collection of images that has only one band, meaning that each image has only one raster file archived with values within -1 and 1, and you can have also here the properties. So let's try to copy and paste some code. You have this code on the PowerPoint. And let's see first an instruction for centering our map. So this is the instruction that you usually give for centering the database or the code editor around a map point. And then the second instruction that we are going to copy and paste and that you have on the slides is this one, print chart. So the print chart instruction is used to print a chart in the right panel. And we can run it, but let's first see the structure of this instruction. So we have to call our instruction. We have to say which is the image collection that is L8_NDVI_composite, that is our variable here, the image collection of Landsat image. We say the region, and we want to generate a time series of normalized different vegetation index on our target, which is the point that I just draw randomly on the map. And we have to apply a reducer. So a reducer is the keyword for saying which data the algorithm should take in case it finds multiple data over the same point. So in this case, we just tell him to take the first data. That is not very important because, of course, as you have seen, the Landsat 8 composite has only one raster file, so you will find only one value and you will take that one. But we will see in the second exercise that this information is relevant if you are working with an area. Then you put the scale. The scale is the spatial scale at which you aggregate your data. So in this case, the scale is 30 because the Landsat 8 data have a pixel size of 30 meters. So we are not basically rescaling our data. Of course, if we put 120 instead of 30, this means that the Google Earth Engine code editor will merge 4 pixels all together. But we don't want to merge, we want to work with the original resolution, so as scale, we just put the resolution of the dataset. We save our script and we run it. You can see here that the system is generating our chart, and we can also, with this button, inspecting our chart. And here you see that we have some data. These data are a little bit scattered because the Landsat 8 was basically sent in 2013, and it has data until 2017 in this database. But what we can do is just to download a CSV file, and we can open this file in Excel. So let me show you. What you basically have is that you just downloaded a time series of data from the Earth Engine. This is quite powerful because basically what you can do with this system is to download a large number of data over a certain point. So this is of particular importance if you think about the revolution that this kind of operation brings into the Google Earth Engine as potentiality of analyzing time series. So before Google Earth Engine, you would have had to download each single Landsat 8 image in your laptop, to process it, to put it on a GIS, and to select the point, and to check the NDVI value in the point. With this system, you just need like 9 lines of coding plus 2 variables that you can basically import just clicking around, and 5 or 6 seconds of calculation for doing a thing that in the life before Google Earth Engine would have need, some days of work. And this is quite relevant for all the application that you could undergo with time series. So this you will find in the slides all the other instructions for this exercise. And now let's do a second operation. So as I mentioned before, what Google Earth Engine can do is to let you import on the cloud your own GIS data, and in particular you can import shapefile. So let's try to do this. So let's click on New, and let's create a new file which we will call exercise 2. So this is a brand new blank file, but rather than selecting our file, clicking around the map, what we want to do now is to upload a file from our laptop. So we go on Assets, and what we do is we click on New, and we go and we upload a shapefile. So I think you more or less have familiarity with shapefiles. These are data from standard GIS system. And what we want to do is to update one area in Ethiopia that I pre-selected. So if you go on the slides again, and you come back to the first slide, and you go basically to the link to data, you will find a compressed folder. You can download it, and you can basically I don't have here. La Francesca non ce l'ha un WinRAR? Okay, we have to unzip. Let's do it. Just 1 second, we will unzip the folder in a while. So basically, here we are again. We unzip our file, our data, and you see that here we have basically the shapefile. So what we can do is to upload our shapefile in Google Earth Engine. We want to upload a shapefile. We go here and we select an asset name. We will call it ODA. Just a simple name, that is the name of the catchment, and then you select the file you want to upload. As you remember, they might be in download here, and we have to select the DBF file, the PRJ file, the SHP, and the SHX file. And we can upload our file. You can see here that the system is uploading your file. This is a quite fast operation in case you have small shapefile to upload. It may be longer, but just you will see that it will take some minutes, and we could see the shapefile in our system. Okay, this actually it's also connected to the kind of use that you made with Google Earth Engine. So consider that multiple users are using Google Earth Engine at the same time, so it might be slow to upload the shapefile. I think it should be. Oh, let's see. Let's wait a second, otherwise we will do the third exercise and then we can come back here. Here you can also check the specification of the shapefile. So while we are doing this, okay, no, in the end this is the Murphy law. When I menace him to move on, he finally uploaded the file. So if you refresh here, you will find that in our asset table we have uploaded a shapefile. So what does it mean? That now we have a shapefile or a vectorial data on the Google Earth Engine cloud system under our user name. So you see that you can analyze the shapefile exactly how we analyze the data that were on Google Earth Engine loaded by the Google team. It's called table, so shapefile in Google Earth Engine are called tables. And you can find here that it tells you where we are, and it gives you also the shape of the shapefile. You can import the shapefile as we imported all the other variables in our program. So let's go ahead. Now we have our data uploaded. And we just have to import the file on the new script, exercise 2. The default name is table, but we will call it again ODA. ODA, very simple name, and we will save our script again. So what we can do, exactly as we did before, we can run again some code to move and to go in another part of the world. Basically, this is a river catchment in Ethiopia. You can see here that this is exactly the same shapefile that I would have in my local system on my GIS, but is basically on Google Earth, and not only on Google Earth, but is ingested in the Google Earth Engine system. So I can make calculation over it. So what we want to do now is not to use again the same database. We are not using again the NDVI by Landsat, but we are loading another one. That is the MODIS Terra Vegetation Index database. And we will call him mod. Let me mention that it's not necessary to call or change the name of variables, but it's quite helpful if you want to have clear coding and you don't want to have mess in your code. So let's try again to print something out from this database. So you see that now the image collection is mod, our image collection. You see that the region is ODA. And you see that the reducer here is not more the first value, but is the mean, because we are working on an area. We are working with data that has a pixel size of 250 meters. That means that we will have a lot of cells within our area, and what we want to do is the mean of all these values. So let's start to run again the script, and you will see that now it will generate a chart. Here you see that it's taking a little bit more time, and this is because we have a little bit more data. The Motis time series is quite more extended than the Landsat. So I anticipate that this operation will take a little bit of time, but is useful to understand what's going on. So you see here the graph. You have a lot of things, and let's just download this data to see how it's made. So here we are. Let's put this data in columns. So you see that here you have the day, the year, and then you have multiple parameters. So you have, of course, some parameters like the azimuth, the solar zenith, but then you have basically like more and more data. You can have the EVI, the NDVI, and so on. So the EVI is the Enhanced Vegetation Index, is another index that you find. And then we have the NDVI here. And I can show you the amount of data that we have just downloaded. So you see, what we basically do, again, and I'm showing everything. So what we basically did in, 11 line of coding is just analyzing 486 satellite image from the MODIS database, and it takes 5 minutes. So you can imagine here the amount of time that you are saving by using Google Earth Engine. So it's what is called a game-changing tool. So just finally, I will make another change in my code. So you see here, I'm basically going to make a modification. So you see here what I did. So what I'm doing here, sorry, I don't think it takes the correct. Sorry, just 1 second. I don't know why it's not getting the correct code. sorry, it was not getting the code, so I modified here by myself. Let's see if it runs properly. So now I'm generating two charts. I will show you the difference. Just when it's finished. But I just invite you to check the properties of the image collection. You see here that this image collection has different bands. So we don't have, like in the Landsat image collection, only the NDVI, but this image collection dataset has multiple images. It does not have only the daily NDVI, but also the enhanced vegetation index and also other variables together. So what I'm doing here is just to tell the Earth Engine code editor to select and print only the data which are called EVI, so the Enhanced Vegetation Index, and the NDVI, the Normalized Difference Vegetation Index. And you can see here that it's also very nice because you see the cycle of the vegetation, how we managed to obtain two graphs with a lot of data, just with the variables that we want. We can also download the image. It's not necessary. It's not necessary to just download the CSV file with the data. You can even just download the image. And let me mention that I'm not like my colleague Saverio, forest scientist. I'm a civil environmental engineer. So the use that I'm doing with Google Earth Engine is just basically to download the time series. So for me, Google Earth Engine is basically a database, but you can see here that with very, very, very few lines, if you compare the past of remote sensing analysis, what you can do is really download an incredible quantity of data in a short period of time. And this, I think, is probably the strength of Google Earth Engine in this phase and as innovative tool for remote sensing. So this is a little bit a snapshot of the potentiality of Google Earth Engine that you can basically use if you want to analyze time series. I'm sorry for the delay. I prepared also another couple of examples, but I think that the priority is to be on time, and luckily we managed to do both the standard application for time series analysis and to show a little bit how the scripts and asset system work. And this is basically, and it's very strange because it's 20 lines of code, but this is basically what you need to know just for downloading data out of Google Earth Engine. So you see that, I think again, the merit and of Noel Gorelick is to have created a tool which is accessible for everyone and which, moreover, it does not require any computational capability apart from a browser. So I think this tool is very useful at all levels, and I hope that you will be able also to engage the Google Earth Engine tutorials online, which are quite well done, and they will explain more or less all that you need to know about this tool. Thank you very much.
Okay, Giulio, thank you very much. We are now ready to close this this day. We have seen several applications. We have seen online examples of application of Google Earth Engine. I would like to close just to announce that here we are going to set up a school of coding for application in remote sensing and spatial analysis, with for sure for Google Earth Engine, but also with other tools such as R. Of course, now we are in the COVID period, so it's not easy to prepare schools, international schools, but you will receive more information soon on these opportunities. So thank you, and bye-bye. And I'm sure that you will find these registration of the morning and the afternoon session on our YouTube channel of the University of Florence. So thank you, everybody.